Alex, entonces una cosa más, cuando yo voy a comenzar, ¿tengo que avisarte antes por mensaje, digamos por WhatsApp? O... Ujú, genial.
Alex, ¿se está viendo la pantalla? Sí. Dame, espérate. Um, ok, ok. Dime si se está viendo el video, la imagen. Sí. Ok. Bien. Bueno.
Ujú, ok. Comenzamos entonces. Um, Hello, everybody, and welcome to another session of this Complex Dynamics Week, organized by 38 Movimientos. We thank you for your presence in today's meeting, and we will start by presenting our first speaker, who is Alberto Castillo. He did his master's studies at Pontificia Universidad Católica del Perú, and he is now a PhD student in the same university under the direction of Alfredo Poirier. His field of study is holomorphic dynamic in one variable. So it's your time, Alberto. Thank you, everybody, for your attention.
Thank you, Abraham. Okay. Well, first I want to thank Alex and all guys of 38 Movimientos for giving me this opportunity to present this mini course. First, I want to say that this is my first talk in English, so maybe I am not the best speaker in English. I beg you for patience, please. Okay. Well, this will be a continuation of the basic course by Professor Poirier. And I will focus on basic tools for understanding the main conjecture, well, I think is the main conjecture of complex dynamics, that is the density of hyperbolic components for rational maps, okay? But I will focus mainly in polynomial families, okay? First, my intention is not to present the most recent research in the field, okay? Because there are greater efforts to tackle this conjecture, but most tools are deep, are technical, and this is not my intention. Okay, I only will present basic tools for understanding the conjecture. Okay, so maybe the expert may feel it is a little bit outdated, or maybe so basic, but well, okay. Okay, here is the program. I will begin with Riemann surfaces, just a little bit, okay? Then a brief recalling of basic dynamics for rational maps. This is the mini course by Professor Poirier, but some things I'm going to recall some things, okay? But then we go very quick to hyperbolic rational maps and some basic geometry, hyperbolic geometry. Then we pass to parameter spaces, and this is the moment when I speak about the conjecture, okay? And then came the tools, holomorphic motions, quasi-conformal mappings, and then we finished today with the paper of Mañez and Sullivan, okay? And this is the program for today. Okay, we now began with the talk. Okay, the context is that of iteration of holomorphic maps, particular rational maps. But in general, these are smooth dynamical systems. Okay, there is a survey by SMAL, differential dynamical system. It's a good survey for beginning with smooth dynamical systems. Okay, in this greater generality, some conjectures for rational maps are not valid for general smooth dynamical systems, okay? But these conjectures may be true for rational maps because of the rigidity of rational maps, okay? And this is what we're gonna do here. Well, okay. Riemann surfaces. This is basic for what? Okay. What is a Riemann surface? It's a connected, oriented, real manifold of real dimension 2 with holomorphic transition maps. What is this? This is something like that. Excuse my terrible pictures. Okay. This is a manifold, two-dimensional manifold. And we have open sets, and we have a chart. A chart is a homeomorphism, okay, between open sets of the surface or of the manifold and open sets of the complex plane, okay. This is the complex plane. Yeah. And maybe we have here some other neighborhoods, some other open sets, and some other chart, okay. And what is a transition map? A transition map is just this. As you can see, a transition map is a map between open sets of the plane, right? And the structure of Riemann surface is due to this transition map is holomorphic. Okay. Well, the first example, very important, is that of the Riemann sphere. Okay. What is a Riemann sphere? It's just the compactification of the complex plane. Okay. Is the complex plane plus a point in infinity. Okay. Now we have to define a topology for this new set. But we have a topology for the complex plane, and now we have to add some open sets, some extra open sets, like this. Okay. The topology of the Riemann sphere is just the open sets of the plane plus sets of this form. That is a complement of compact sets of the complex plane plus this point at infinity. Okay. You should verify that these sets form a topology. Okay. Now we define a topology for this new set, Riemann sphere, and now we need an atlas. And in this case, the atlas is very simple, just two charts. Okay, two charts. And one chart is just the the circle of radius 2 with the identity, okay? And the other chart is the complement of the circle of radius 1.5 plus the point at infinity. And the map is like this: 1 over c for c distant to infinity, and 0 for c equal to infinity. With this pair of charts, we have a Riemann structure, a Riemann surface structure for the Riemann sphere. Okay. Well, now functions between Riemann surfaces. If we have two Riemann surfaces, a map is holomorphic if it is so in local charts. And what does this mean? Again, we have the two Riemann surfaces and a map. Okay, let's this point and the map that take us to this point. Here is a neighborhood, an open set, and here is also an open set. We have a chart. We have a chart. Okay, this chart is a homeomorphism with an open set of the plane. And the same for here. An open set of the plane, okay? And now we have this function. Okay, -1. And this is clearly a function with open sets of the plane. And this function, if it's holomorphic, then we say that f is also holomorphic. Okay, so the properties of f, we read it locally. Okay, that is with charts. We read it in charts. Well, this is a holomorphic map. And if this map is a homeomorphism, we say it is a conformal isomorphism or B holomorphism if this map is also holomorphic. Okay, that is, if this function f is a homeomorphism between S and S prime, we say it is a B holomorphism if it is also holomorphic. Okay, so B holomorphism is homeo plus holomorph. Okay. Well, in this case, that is, if we have a function, a B holomorphism with two Riemann surfaces, we say these Riemann surfaces are conformally equivalent. And this is the right notion of equivalence between Riemann surfaces, okay? And if we have a conformal isomorphism of a Riemann surface with itself, we say it is a conformal automorphism. And here we have an example of conformal isomorphism, and this is between the disk and the upper half plane. Okay, both sets are clearly Riemann surfaces because they are subsets of the plane. Okay, and the conformal isomorphism is given by this function. Okay, this function establishes a B holomorphism between the half upper plane and the disk. Well, this is a great theorem. This is the uniformization theorem that says this, that there are only three simply connected Riemann surfaces up to conformal equivalence. That is, up to a B holomorphism between the Riemann surfaces. And these three simply connected Riemann surfaces are the disk, the complex plane, and the Riemann sphere. Okay, these three surfaces are clearly different. the Riemann sphere is clearly compact, the disk and the complex plane are clearly not. Also, by trivial theorems from complex analysis, we know that the disk and the complex plane are not conformally equivalent. Okay, so I think this is clear that these three Riemann surfaces are different, right? Well, now we see a conformal automorphism of the disk. This is the rotation. It's clearly a conformal automorphism of the disk. Well, this is important. The conformal automorphisms of the three simply connected Riemann surfaces. Okay. For the Riemann sphere, the group of conformal automorphisms is given by the Mobius transformation. Okay. For the plane, this group of conformal automorphisms are the affine maps. Okay. These are the affine maps. It is clearly a subset of the Mobius transformations. And for the half upper plane, the group is the Mobius transformations with real coefficients and positive determinant, really determinant equal to 1. Okay, and this is okay. And so what we have until here, we have classified the simply connected Riemann surfaces, the disk, the plane, and the sphere. But also we have the group. We have the group of conformal automorphisms of all these three surfaces. Okay, and this is important for certain reasons that now we are going to see. But first, we need some tools from topology, more particular from algebraic topology. Maybe some of you know it, but I will going to recall it. Okay, two topological spaces, a map between this X and Y. And we say this map F is a local homomorphism if for any point in X, we have a neighborhood of X such that the restriction of F with respect to that neighborhood is a homomorphism onto its image. We say F is a covering map if for all elements in Y, we have a neighborhood such that the inverse image of the neighborhood is disjoint unions of open sets, and all of these open sets are homomorphic to the neighborhood in Y under the function. This is very simple. We have a function F between a space, a topological space X, Y. Okay, and we have a covering map if for any point we have a neighborhood here, and the inverse image of this neighborhood is a pile of neighborhoods here, disjoint neighborhoods, but all of these neighborhoods are homeomorphic to be under F. Okay, that is, we have this. Okay, right? Okay. Associated to a covering map is a deck transformation. A deck transformation of a covering is a homomorphism of X such that we have this. Okay, this is something like that. Again, we have a covering map. And what is a deck transformation is something like this. It's a homomorphism such that it takes a point and take it here, and then came F, and this diagram commutes. That is, we have F of the evaluation of the point X under the deck transformation, and it is equal to Fx. Okay, if this is true, then this map is a deck transformation. Clearly, the deck transformation is a group with respect to composition. Okay. Now, we say a covering is normal if for any pair of points in X such that the image under the covering map is the same, then there exists a unique deck transformation that takes one point into the other point. So this means something like this. If I have a point X and a point X prime, the image under F is the same, that is Fx equals Fx prime, there must exist only one deck transformation that makes this. Okay? If this is the case, we say the covering is normal. Or some another name for this is that the covering is Galois. Well, this remark is very useful. Any covering map is a local homeomorphism. The converse is not true. But if we suppose the map is also a proper map, we have the next result. A proper local homomorphism is also a covering map. Okay? Then we have this notion of fundamental group. Maybe all of you know it. It's just the homotopy classes of loops based at the point X. And why I made a recalling of all these things? Because there is a parallel between the fundamental group and the covering of a manifold, or well, of a topological space in general. Okay. And now we specialize to Riemann surfaces. Okay. Well, recall we are talking about connected Riemann surfaces. Okay, and since the Riemann surface is connected, we have a universal covering. That is a covering map such that this map, this topological space is tilde, is a simply connected topological space. Okay, this is a universal cover. In this case, recall S has Riemann surface structure, and then the universal covering manifold inherits the Riemann surface structure of S. And this is because we have this map is a local homomorphism. So if we have this construction, excuse me, still that S, and we have a Riemann structure here. That is, we have these charts, and since this P is a local homomorphism, we have open sets here and open sets here. This is homeomorphic. This is also a homeomorphism, and composition is also a homeomorphism. And now we have charts for this topological space. Okay, well, in this case, the deck transformation group of the universal covering is isomorphic to the fundamental group of S. Okay, this is like here. This Riemann surface as a fundamental group, okay? And since this is a covering has its group of deck transformations, okay? And we have this result that this group of deck transformation is isomorphic to the fundamental group. Okay. Well, the universal covering is always a normal covering. Recall what is a normal covering, it's here. And so in this case, we can identify the Riemann surface S with this quotient. That is, S is isomorphic to a quotient of S tilde with the group of deck transformation. Right? Well, this is some example with the puncture disk. Okay, we have this map. This is the half left plane. I'm going to make a picture here. We have the complex plane, and this is the half left plane, right? Once again, excuse my terrible pictures. Now we have a map. With the puncture disk. Okay. This map, this F, the exponential, is a covering map. Okay. The group of transformation of deck transformations of this covering is free and is a cyclic group, and is generated by the translations. Okay, and this is just because the inverse of the exponential is the logarithm, and well, this group of deck transformation associated to this map. Okay, and well, this group is clearly the set of integers, or is isomorphic to the set of integers. So by the result of here, we know that the puncture disk is isomorphic to this half left plane, quotiented by this group. Okay. Okay, but what happens if we begin with one of the three simply connected Riemann surfaces? That is, being the disk or the complex plane or the Riemann sphere. And recall, for these three Riemann surfaces, we have a group of automorphisms. Okay, so what happens if we take a subgroup of this group? Under what conditions for this subgroup we may have a Riemann surface making a quotient? For example, under what conditions for this subgroup, if we quotient the disk with respect to this subgroup, we have a Riemann surface? There are two conditions, okay? Well, but first we need a normal covering. Recall that in this case, we have a normal covering, and we can express the Riemann surface X with the quotient. So what we need here? We need two conditions. The first is that the subgroup acts properly discontinuous, okay? And also that it acts freely, that is without fixed points, right? If these two conditions hold, then we have a normal covering, and the covering map is just the projection with respect to the group, okay? In this case, these two conditions, in particular, the first condition, the properly discontinuous condition, imply that that this subgroup must be discrete. Okay, discrete with respect to the topology that the automorphisms group inherit for being a subset of the Mobius transformations. Okay. Well, there is this definition that is important. That is the row classification of Riemann surfaces according to what is the universal covering. If the universal covering of a Riemann surface is a disk, we say it is hyperbolic. If it is the complex plane, we say it is parabolic. Or if it is the Riemann sphere, we say it is elliptic. Okay. Well, examples, in this case of parabolic surfaces, well, so we go to the complex plane, right? What we're looking for in the complex plane. First, recall the automorphisms of the complex plane. These are maps like this. Okay. A subset of the Mobius transformations. Well, what we look for maps that act freely, okay, and to be discrete, okay. Acting freely is that it acts in C with no fixed points, but we have this. Okay, look. What we have here, this is a fixed point. This cannot happen because we need that the maps act freely. So we need that A equals to 1. In this case, we have no fixed point, right? Well, for that reason, we restrict to maps of this form, okay? But also, as I said before, here, the properly discontinuous condition imply that the subgroup must be discrete. So this subgroup of maps of Mobius transformation must be discrete. And this only happens in two cases. First, when the subgroup is cyclical, in this case is isomorphic to the integers, or is generated by two linearly independent complex numbers, linearly independent over the real numbers, okay? So we have two cases. One case is if we quotient the complex plane with respect to the integers, we have a cylinder, okay? A cylinder is conformally equivalent to the puncture plane or to the sphere minus 2 points. This is the same. This is clearly the same, okay? And otherwise, that is for the case of two linearly independent complex numbers, okay? We have a lattice that consists with this group, okay? This group with two generators. First, with translation with respect to the unity. Okay, and this other group with translation with respect to a complex number with imaginary part positive, strictly positive. Okay, we made a quotient here. The quotient of the complex plane with respect to this group is a torus. Well, the example that we like is that this complex torus. Okay. Okay. For the elliptic surfaces, recall here the classification. We talk about parabolic, and for the elliptic case, there is only one elliptic Riemann surface. That is the same Riemann sphere. Okay. The most important example is that of the hyperbolic Riemann surfaces. In fact, almost all Riemann surfaces are hyperbolic. Okay. We care about this case, that is the hyperbolic surfaces of the Riemann sphere. Okay. Well, the Riemann sphere we know is elliptic surface. Okay. If we remove a point, well, we have the complex plane. Okay. And if we remove 2 points, we have a puncture plane. This is a parabolic surface, clearly parabolic. And this is the puncture plane we talk about here. Okay, this is also a parabolic surface. And if we remove another point, this is not elliptic, clearly not elliptic, clearly not parabolic. We say that the only parabolic surfaces are the complex plane, the puncture plane, and the torus. So what is left? This is left to be an hyperbolic surface. Okay. If we keep removing more points, we also have hyperbolic surface. Okay. Well. Okay. Well, this is all with Riemann surfaces. But what I did this presentation about this basic thing, this is because Professor Poirier in his course made this dynamics for subsets of the plane. But the dynamics can be performed in Riemann surfaces. Okay. And we are here we are interested in the dynamics between the sphere, between the Riemann sphere. Okay. A function, a holomorphic function between the Riemann sphere is what we call a rational map. Okay. All of us knows how is a rational map. Okay. And we are interested in iteration of these rational maps, degree at least 2. Okay. And now we recall the basic in dynamical objects. Professor Poirier made a full details of all these things, but now we recall some just a little bit. Okay. The Fatu set is the set of points such that the iterations of the map is a normal family. The Julia set is the complement of the Fatu set. Recall that both of these sets are totally invariant. Okay. And now we come these special and important objects, the critical points and the periodic orbits. Okay. In rational maps, degree D, we have D 2D minus 2 critical points. Okay, and the critical points are important because they determine the dynamics of the function. Okay. Then we have the postcritical set. This is just the closure of the critical orbits, but with exception of the critical points. That is, if we have a critical point here, critical point, and we take the orbit of the critical point, and so on. This set is the postcritical set. Okay? But we take closures. We take the closure of this set. Okay? This is the postcritical set. So there are two fundamental objects. First, the critical points, and then the periodic orbits. Okay, first I talk about the role of the periodic points. Well, recall a point is periodic if we have this. The iteration of the map of this point is equal to this point. In this case, we say that C is M periodic. Okay. And we have something like this. The points here are the periodic cycle. Okay. Well, for a periodic cycle, we have this special number that is the multiplier. Okay, that is just the derivative with respect to any point of the cycle. Okay. And recall that we have a classification of periodic cycles according to the multipliers. We say the cycle is attracting if the modulus of the multiplier is less than 1, and super attracting if the modulus is 0. The cycle is repelling if the modulus is greater than 1, and it's indifferent if the modulus equal. And in this last case, we say the cycle is parabolic if the multiplier is a root of unity, and the indifferent cycle is irrational if it's not a root of unity. Okay. The multiplier of the cycle is important because it determines the local dynamics of such points. Suppose we have here a point C, and this point C is n-periodic, okay? Suppose, for example, that it is attractive. Okay, so the multiplier, the modulus of the multiplier is less than 1. Okay, a theorem says that the dynamics of Fn is conjugated to this linear dynamics. Okay, look, here there is a local conjugation. So the local picture of the function, or well, of the n iterate of the function, is that of a linear map. And the coefficient is just the multiplier. okay? And this happens not just for attracting cycles, but also for repelling cycles, okay? But I forgot to tell it here, attracting but not super attracting, okay? Not super attracting. For super attracting cycles, we have a theorem, that is the Butler theorem, that says that the map, the iteration of f is behaves like this this map. Okay, so for super attracting cycles, this is what happens. Okay, and this is a conjugation. So as you see, we have a local picture for what happens with attracting and repelling cycles. In the case of indifferent cycles, is another history. Okay, but in the case of irrational indifferent cycles, we have two types of periodic points. The irrational periodic points may be Siegel or Kremer, according to if a linearization is possible or not. For Siegel irrational points, the linearization is possible, but for Kremer, it's not. Another difference is that Siegel points belongs to the Fatou set, but Kremer points belongs to the Julia set. Okay? Well, this is the local picture according to the periodic points. Fixed points are important, okay? They play a fundamental role in the dynamics. Recall that for degree D rational maps, we have D+1 fixed points. And we classify these fixed points not just according to the multiplier, but also to its multiplicity, okay? The multiplicity is just the order of vanishing of this polynomial, of this map. Suppose we have a fixed point, okay? And we have this equation. And we did this. And this, if we made a Taylor approximation, okay? The order of vanishing along this point, this is the multiplicity of the fixed point, okay? If the multiplicity is 2 or more, the fixed point is parabolic, okay? Well, this was the local picture according to the periodic points, and now we go to the global picture. Well, there is a very known result that says that the Julia set is the closure of the repelling orbits, okay? And what happens with the Fatou set? Recall that the Fatou set is fully invariant, okay? And the Fatou set is an open set, and so we have components, open connected components of the Fatou set. Well, the rational map takes one component onto another component, okay? So there is a dynamics of components in the Fatou set. To understand this dynamics, we have the next theorems, okay? First one theorem for fixed components. Suppose you have a Fatou component that is fixed, okay? So what are these fixed Fatou components? These fixed Fatou components can be just of 4 types. These are immediate basings for attracting fixed, for an attracting cycle, or maybe is a parabolic basing for a parabolic fixed point, or is a Siegel disk, or is a Hermann group. Okay, we just have just these 4 types of Fatu components, of fixed Fatu components. Okay, the same is true for periodic components. Recall just that if you have a Fatu component, okay, and that if it is periodic and periodic, okay, well, U is fixed. U is fixed for Fn. Okay, so we just see at this first theorem for fixed components, and there is. Okay. Okay, so now we have seen how are the periodic Fatu components. Okay, and maybe we have some pre-periodic or eventually periodic Fatu components. That is, Fatu components that are eventually mapped to some periodic cycle. Okay. In this case, I think the dynamics is very clear. We have cycles of Fatu components. This is an cycle. And a Fatu component may be pre-periodic, so it is mapped by Fm, say, into a cycle. This is pre-periodic. And these are periodic. Okay? Until here, we have the classification of periodic and pre-periodic Fatu components. Okay? And what happens if there is a Fatu component that is not pre-periodic? The answer is simple. There is no Fatu components that are not pre-periodic. That is, all Fatu components are periodic or pre-periodic. And this is because of the Sullivan no-wandering theorem. Okay? But this is a deep theorem. Okay? So this is the global picture of Fatu components. Well, recall that I said that there are 2 important things. One is periodic orbits, and the other is the critical points. So there is an interplay between the critical points and the periodic cycles. Okay. First, if one have a critical point in the Fatu set, okay, this critical point converts to an attracting cycle or to a parabolic cycle. Okay. If the critical point belongs to the Julia set, in this case, the behavior is more intricate, it's more complicated. Okay. But here is the relationship between critical points and periodic cycles. Okay. This is a theorem, an important result that says that we have only a finite number of non-repelling cycles. Recall all the types of cycles: attracting, repelling, indifferent. But this theorem says the vast majority of cycles are repelling, and there is just a little bit of non-repelling cycles. Okay. There are bounds for the number of non-repelling cycles, and in particular, a result of Shishikura, but he uses this technique of quasi-conformal surgery. There is not a simple technique, it's not elemental. He puts a bound for the number of non-repelling cycles, 2D minus 2. Okay, this is the number of this thing attracting or indifferent cycles. Okay, but there we can get a bound not so sharp like this, but a bound, an useful bound, if we use more humble techniques. Okay, you can see the details of this thing in chapter 13 of the book of Milner, okay, the book of dynamics of one complex variable. Well, now we see what happens with the postcritical set, okay? Recall the postcritical set is the closure of the critical orbit except for the critical points, okay? This set is invariant, okay? Also contains the attracting orbits of the function. This is true just because we are taking the closure, okay? I know in some definitions of the postcritical set, they don't take the closure, but I am taking the closure. If we take the closure, the postcritical set contains the attracting orbits, okay? Also, it contains the Kramer points and boundaries of Seigel disk, okay? Okay. For the postcritical set, we have important geometric features when this set is not too big. And I am going to explain this thing, but first we need some background from geometry, okay? But this is very simple, okay? Well, recall that the Riemann surface is a smooth manifold, okay? So in this case, we can define a Riemannian metric, okay? We all know that the Riemannian metric is an inner product defined for all time spaces, okay? If we take subsets of the plane, this Riemannian metric is defined by a positive definite matrix that defines a quadratic form. And recall that these functions here are real smooth functions, okay? And we say the metric is conformal, okay, if these elements are 0 and the elements here of the diagonal are equal, okay? So in this case, we can define the metric. So, if these conditions hold, we can define the metric as this, okay? A function of the variables x and y and this construction here, okay? But as we are working with complex variables, we take the usual setting, okay? And in this case, and also if we write this function as the square of a smooth and positive function, we get this result, this representation for the metric. This is a Riemannian metric that is also conformal, okay? Well, some definitions are necessary. If we have a subset of the plane, we have an isometric with respect to this conformal metric here. This metric is of this set U, okay? We say this function is an isometry if we have this condition, okay? That is, if something is measured in the domain, the same is true in the range, okay? Okay. We have a very related concept that is of invariant metric. We say a metric is invariant under a conformal automorphism if the equation above holds, okay? If this is true, for a metric, okay, we say this metric is invariant with respect to the function f. Well, now we define the preferred metric for the disk, okay? There is only one Riemannian metric on the disk, which is invariant under the conformal automorphisms of the disk, okay? And this is the Poincare metric or the hyperbolic metric. And this is the metric, okay? And this metric was chosen so that the Gaussian curvature equals to -1, okay? Well, this is the preferred metric for the disk. We have these other conformal metrics, but they are not suitable for the disk. We have the spherical metric, okay, and the Euclidean metric. This is the the standard metric, okay. Well, this metric is the metric of the disk. That is, this is the metric, something like this, okay? We have a Riemann surface S. Suppose this is a Riemann surface hyperbolic, okay? Clearly, this is covered by the disk. Recall this is a covering map, a universal covering, okay? We have a metric here, okay? And well, we like to define a metric for this Riemann surface, okay? So we have this, okay? Recall that there is a projection. This projection is the covering map, okay? And there is only one Riemannian metric on the Riemann surface S that makes the projection a local isometry. And this is the Poincare metric on S. That is, we have a metric for D, for the disk, and we look for a metric here in S such that P is a local isometry. Okay? And the metric in S that makes P a local isometry is the Poincare metric for S. Okay? Well, the next result is very important. This says that the hyperbolic metric is contrast. Okay? If we have two hyperbolic Riemann surfaces and a holomorphic function between them, then only one of the three options happens. Okay, it can happen that F is a conformal isomorphism and an isometry. Okay, or F is a covering map, not injective, but is a local isometry, local, not global isometry. Okay, or it may happen that F strictly decreases all non-zero distances. Okay, only one of these three options. Okay. And here we have an example of an isometry. Again, recall this map that is a B holomorphism between the half upper plane and the disk. Okay, this map. Well, and this map is an isometry. Recall that in this case we have this. Okay, this is the definition of isometry. This is here. Right? In this case, this is the map. Okay, C equals to this function of W. And well, now we make some trivial calculations. Okay. And we get the Poincare metric for the half upper plane. That is, I have the Poincare metric for the disk, this is, and using this isometry, we recover the Poincare metric for the half upper plane. Okay? Here are another examples. And in this case, we have a covering map. This map, the square of C, defined in the puncture disk, is a 2-to-1 covering map, okay, of the disk to itself. Okay, and this is a local isometry. Okay, this is a local isometry. So this is the second case here. For the third case, we can define just the inclusion. Okay, the inclusion is clearly holomorphic and injective, but not conformal. So it's not conformal, it's injective, so it's 1-to-1. So we are not in the second case. So we only have the third case. So in this third case, the inclusion must satisfy that it strictly decreases all non-zero. Okay. Well, this was a brief geometric recalling. And now we return to the postcritical set. Okay. Suppose we have a rational map of degree at least 2. And suppose the postcritical set has 3 or more elements. Okay. And if the postcritical set has 3 or more elements, then the sphere minus the postcritical set is a hyperbolic Riemann surface. Recall what we said before. No? The hyperbolic surfaces of the sphere are just the sphere minus at least 3 points. So this set is hyperbolic Riemann surfaces, and we can define here a hyperbolic metric. And with these conditions, we have this result. This is the expansion of the Julia set. Okay? Suppose you have a Julia point, which orbit is disjoint from the postcritical set. Then for the hyperbolic metric, we have that the derivative at this point, the derivative of the iteration, okay? If we iterate more and more and more and more, then the norm of this derivative with respect to the hyperbolic metric tends to infinity, okay? Well, I talk about dynamics of rational maps, but now we pass to polynomial dynamics, okay? For polynomials, some results, we can get sharper results, okay? For example, for the Fatou components, recall that for rational maps in general, the Fatou components are attracting basins, parabolic basins, Siegel disks, or Hermann rings. But for polynomial maps, we don't have Hermann rings, okay? There are no Hermann rings. Also, in polynomials, polynomials are defined in the complex plane, but we can naturally extend polynomial maps to the Riemann sphere, just saying that infinite goes to infinite. Okay. Also, for polynomial, we have a field Julia set. Recall that field Julia set is just a set of points with bounded orbit. Okay. This set is compact, completely invariant, and full. Recall full is the complement is connected. Okay. And the complement of the field Julia set in the sphere, the complement in the sphere, is the basis of attraction of. Well, this point at infinity is really important because we can define or we can use the Butcher theorem and define a conjugation of the polynomial in a neighborhood of infinity. Okay? If the polynomial has degree d, we can have a conjugation with this map. Okay, zeta d. And this conjugation is valid in a neighborhood of infinity. And in the case, if the field Julia set is connected, okay, the complement, okay, I said, if the field Julia set is connected, this isomorphism can be extended to the whole basin of attraction of that is to the complement of the field Julia set. Okay. I will explain it here. Suppose this is the field Julia set connected. Okay. I know this doesn't look like a field Julia set, but okay. And this is the basin of infinity. And if this set is connected, we can define a conjugation of the polynomial with this map. Okay, this conjugation is valid in this. Okay. And here, this is an isomorphism, the Butcher isomorphism. And this is just the complement of the disk. Okay. So the local picture of the function in a neighborhood of infinity is like this function. Well, we can foliate this complement. Okay, there is two foliations. There are two ways to foliate. Okay, one is with equipotentials. And to define equipotentials, we need a function that is the green function. The green function is just the logarithm of the modulus of the Butcher map. Okay, the Butcher isomorphism. This is the green function. This function is harmonic and satisfies this identity. Thanks to this identity, we can define the green function in the whole basin of infinity. Okay. And thanks to this green function, we can define equipotentials. And how is this? It's more or less like this. The green function of a point is just this. So this point, and this is the Butcher map, okay? We have the disk, and maybe this point belongs to this, okay? This is the image of the point. And here we have a radius. We have a radius. Okay. So the green function says this point has this potential. Okay? The green function defines potential for a point. In this case, we say the green function of C equals logarithm of R. Okay? And clearly the green function takes points in the complex plane to real points. Okay, so we can define equipotentials. Level curves, okay? We take a point here, a potential, a real number, a real positive number, okay? And we form here the set of points that has the same potential. Okay? This is the equipotentials. And with these equipotentials, we can form a foliation of the complement of the field velocity. Okay? This is one foliation, but we have another foliation that is by means of rays, external rays, but I will define it later. Okay? Well, this is a basic result. The connectedness of the Julia set depends on the critical points. Okay? This is basic. The Julia set is connected if and only if the field Julia set contains all critical points. This is a basic result. Okay? Well, now we pass to what is a hyperbolic map. Okay? Well, degree at least 2 rational map is hyperbolic if one of any of the next conditions, these are equivalent conditions, okay? All critical orbits converge to an attracting cycle, okay? Or the postcritical set and the Julia set are disjoint, or the map is expanding in the Julia set. And this means that we have a conformal metric in a neighborhood of the Julia set, such that the norm of the derivative with respect to that metric is greater than 1 for all points in the neighborhood. Okay, we have these 3 equivalent conditions of hyperbolic map. Maybe the most simple of this condition is the first. Okay, all critical orbits converge to an attracting cycle. So, what does mean, or what is an hyperbolic map? We understand it more or less like this. Okay, recall that critical points define the dynamics. Okay. Well, so if we like to control the dynamics, we must have control over the critical points. Okay? If we like to take control of over the dynamics, we must have to take control over the critical points. Now, suppose that any critical point is attracted to an attracting orbit. Attracting orbit, and all critical points are attracted to these orbits. What this means? This means that we have control over the critical points. Okay? So, hyperbolicity means we have control over the points that controls the dynamics. Okay? This is more or less the meaning of hyperbolicity. See this condition here. Postcritical set is disjoint for the Julia set. what this means. Recall that Fatu set is the normal set. Normal that can be interpreted as predictable. Okay? And why this is predictable? Recall that before I say this, we have a global picture, okay? But two components are this, and that's all, okay? So in the Fatu set, we have total control. The dynamics is predictable, okay? In some sense, the dynamics is trivial in the Fatu set. But this does not happen with the Julia set. The Julia set is the chaotic set, okay? We don't know what happens in the Julia set, okay? And suppose that the postcritical set does not intersect the Julia set. Suppose the postcritical set is here, okay? So in this case, what happens with the critical points keeps far away from the chaotic set, okay? The points that control the dynamics are far away from the chaotic set. So this is good, no? This is good. But what happens if the postcritical set touches the Julia set? Or even worse, maybe a critical point belongs to the Julia set. If a critical point belongs to the Julia set, well, this means that a point that controls the dynamics is into the chaotic set. And this is clearly not good. Okay? In this case, we don't have hyperbolicity. So what you have to understand is that hyperbolicity is the same as we can control the dynamics, or the dynamics is some or less trivial, okay? Well, thanks to hyperbolicity, we can get the next, for examples, the next result, okay? If the rational map is hyperbolic, all periodic orbits are repelling or attracting, okay? The Julia set of a hyperbolic map with connect Julia set is locally connected. This is important, okay? This is very important. The locally connectedness condition of the Julia set, okay? Maybe until this point, you may not understand why it's so important, the locally connectedness of the Julia set, but believe me, it's very important, okay? Another condition is that hyperbolic maps are stable. I am going to explain what is stable, okay? But these conditions are important, okay? Well, there is some results by measure theory that are also important in this context of hyperbolic maps. First, a definition. We say a rational map is ergodic if for any measurable set that its inverse coincides with the set itself. If this happens, if this condition is true for some measurable set, then this measurable set must have zero or full measure in the Riemann sphere. All measures are Libert measures, okay? Lebesgue measures. Well, and this is important because thanks to this, we can get the next result that is valid for hyperbolic maps. Okay, the Julia set of a hyperbolic rational map has measure 0. Lebesgue measures. Okay, this is true for hyperbolic rational maps. Well, this is a concept I would like to explain this. Okay. I said that the Julia set of a hyperbolic map that is connected is also locally connected. Okay. And I said that this result was very important. Okay. But to obtain this result, we do not need the strength of a hyperbolic map. We can relax some conditions and equally get this result. Okay. So this result is true for a little more less than hyperbolic maps. Indeed, this is true for these maps that we call sub-hyperbolic. Okay. And I'm going to explain this. Okay. Recall hyperbolic map means that we have control over the critical points. Okay. So what happens, for example, if we have a point, a critical point in the Julia set? In this case, well, the critical point belongs to the chaotic set, and we think all is lost. All is lost. But not necessarily true. Why? Because this critical point may be pre-periodic. Not periodic, obviously, but just pre-periodic. Okay? In this case, even if the critical point belongs to the Julia set, it must eventually converge to a repelling cycle. Okay? This is a repelling cycle. Okay? And well, if the critical point is pre-periodic and converts to a repelling cycle, so maybe the critical point belongs to the chaotic set, yes, but we can still recover certain control because this point is eventually mapped to a repelling cycle. So the critical point we have certain control, okay? So in this case, that we have some control over the critical point, we can still recover some of the features of the hyperbolic maps. And this is the case, for example, of the sub-hyperbolic maps. Okay, so what is this map? This a rational map is sub-hyperbolic if and only if every critical orbit is finite or converges to an attractive periodic point. This condition, every critical orbit is finite, is something like this. No? In this case, the critical orbit of this point is finite because it ends in a repelling cycle. Okay? Maps like this are sub-hyperbolic. And we have the next result. We have a sub-hyperbolic rational map with connected Julia set. In this case, the Julia set is also locally connected. Okay? Now, there is a geometric definition of subhyperbolic map, but you can see it in chapter 19 of the book of Milnor, and also in the Orside notes of Duady and Hubbard. Okay, what I just want to recall is this theorem that characterizes this subhyperbolic maps. Okay, well, now I talk about parameter spaces. Because I am getting near to the conjecture. The conjecture that is the objective of this talk is something like this. We have a parameter space of rational maps. Okay. And some of these functions of this parameter space are hyperbolic. Okay, so you can see something like this. This is the rational maps. Okay, here we have the subset of hyperbolic maps. Okay, I want to know how is this set of hyperbolic maps with respect to the set of rational maps. And we see it in the parameter space. Okay, well, the degree D rational functions that I name it RAT D, okay? This is a subset of the projected complex space 2D plus 1, okay? And we are interested in families of degree D rational maps. That is subsets of this complex projective space, okay? A family is just a subset of rational maps, okay? And we see this family as a function like this, okay? Suppose we have a subset, in general, is a subset of rational maps, okay? A family is just a function, okay? It's like a bivariate function, okay? And this map is defined as this, okay? This is just and these functions are rational, okay? This is a family of rational. Well, this set is the parameter space of the family, okay? We usually require that this set to be an open connected subset, okay? Well, but also we like to impose some extra conditions of parameter dependence. I will explain it later, okay? But the examples that I will give in the next talk tomorrow are more concerned with polynomial families, okay? In the case of polynomial families, we introduce some subdivisions in the parameter space, okay? For example, if we take a family of polynomials, first put par f for the parameter space, okay? But our parameter space for polynomial families will usually consist with some product of the complex plane. We usually work with the complex plane or C2, but in this talk, I only will work with the complex plane, okay? Okay, there is a special subset of the parameter space that is the connectedness locus. What is the connectedness locus? It's just the set of parameters such that the Julia set of this parameter is correct. The complement of the connectedness locus is the escape locus. Okay, this is the set for which at least one critical point escapes to infinity. And recall that this, in the context of polynomial, says that the Julia set is not connected. Okay, so what we have in polynomial families? In polynomial families, we have something like this. Okay, we have subsets, parameter spaces. Let's say this is the set of parameters. Okay, and we have a connectedness locus that is Julia set connected. And an escape locus. This is a complement. In this case, well, is Julia set is not connected. Okay. And we can even get subdivisions of the connectedness locus or the escape locus, but it will depend on the family. Okay. And now we see a pair of examples, but in particular the first example, that is quadratic polynomials. Okay. We see that any quadratic polynomial is conjugated by an affine map to a polynomial of this form. Okay. So we have this family. We have a family of maps like this. In this case, the parameter C can be any complex number. So the parameter space is just a complex plane. Okay. In the complex plane, we have a connectedness locus and an escape locus for this family. Okay. And the connectedness locus for this family is the well-known Mandel set. Okay. So this family of quadratic polynomial maps has connectedness locus this set. The complement is clearly the escape locus. Okay, this set blue, light blue, right? Well, but this is the subject of the next talk tomorrow. Okay. In this case, this is a uniparametric family. That is, it depends on just one parameter. Okay. But we have families that depends on two parameters. For example, this cubic family, cubic maps, okay? This has two parameters, A and B, okay? So in this case, the parameter space is C2. But now the things get complicated. The connectedness locus really has a complicated topology, and the escape locus too, okay? And in this case, the escape locus is, we have a foliation, or a subdivision of the escape locus by a foliation. by hypersurfaces like this that are homeomorphic to the sphere S3. Okay, this is a result by Brunner and Hubbard. We have a paper of this. Well, okay. Well, in the parameter space, we can define equivalence notions. Okay, and these equivalence notions depends of the conjugation of two rational maps. This is something like this. Okay, we have a rational map here, another rational map here, and we can define a conjugation. Okay. What? This conjugation is basically an homeomorphism, but if we impose extra conditions of this on this conjugation, we can get better results. Okay. We say the conjugation is conformal if this map is a Mobius transformation, is topological if this map is a homeomorphism, and is quasi-conformal if this map is a quasi-conformal map. Okay? The conformal conjugation is a strong conjugation. It's very rigid. Okay? The topological conjugation is in the contrary for this. Is not rigid, and the quasi-conformal conjugation is in between the two. Okay, and the best conjugation is quasi-conformal because is, as I said, is not so rigid. Okay, as conformal conjugation, but I have to explain what is a conformal conjugation. Okay. Okay, we will define it in the next minutes. Okay. Well, now the conjecture. Okay. Well, for the degree D rational maps, we have a set of hyperbolic maps. Okay. And what can we say about the set of hyperbolic maps? We have this conjecture that hyperbolic maps are dense among all rational maps. This is the hyperbolicity conjecture. So the density of hyperbolic maps in the set of rational maps. Okay, this says that we can approximate any rational map via hyperbolic maps. Okay. This conjecture is false if we take just smooth maps. Okay, in smooth maps, this is false, but in rational maps, there we have best properties. These conjectures may be true. Okay. Well, this one of the first approximations to this conjecture is by a paper of Menyesat and Sullivan. Okay, when they work a very similar result. Okay, and to understand this, we need certain tools. First, we need to understand this condition. There is structural stability. Okay. Well, we say that a rational map is structurally stable if we have a neighborhood of the map, obviously a neighborhood in the parameter space, such that all functions in that neighborhood are topologically conjugated to the map F. Okay, this is something like this. We have here the space of rational maps. Okay, and we have here a rational map F. This is the parameter space. And if we have a neighborhood of F such that all other rational maps in U are such that F is topologically conjugated to G. Okay? In this case, we say F is structurally stable. Okay? And precisely, there is a great result for structurally stable maps, okay? But to understand it, we need some tools. And the tools are basically two. First, holomorphic motions and quasi-conformal maps. Okay? Well, first, what is a holomorphic motion? Well, to make it simple, just do it like this, okay? Suppose you have a subset of the plane, okay? In general, it can be a disk, okay? And we define a function, a set of functions, a family of functions, depending of this disk, okay? Well, okay. First, we're interested in a subset E of the sphere. Okay, and we are defining maps on this set. But these maps will depend on parameters here in this. Okay, and this family of functions satisfy the next properties. Okay, first, that we must choose a basic point, a base point that we say in this case will be 0, okay? F0 is the identity map. That is, F0 takes E in E, okay? This is F0. And the other functions, F lambda, are injections, okay? Injections. So the set E is, and this is the image of E under this map, okay? And we also need the next condition. If we fix a point C in E, then this map is holomorphic in lambda, okay? F lambda is just an injection. It must be holomorphic, just an injection, okay? What is a holomorphic map is F with a fixed point a fixed C here, but the holomorphicity is with respect to lambda, not with respect to C. Okay? In this case, we say this family is a holomorphic motion of the set E. Okay? This is the condition. Well, this is for what? Holomorphic motions are used to define deformations of a set. Okay, really, a holomorphic motion is an isotopy of the set. See, again, here we have a set E and a family of functions. A first function, the identity, F0 is the same E. Okay, but the other functions are injections. And what they do is deform this set E. Okay, but the deformation is holomorphic. Okay, this is the particular condition of holomorphism. So you can see it as two variables. No? With respect to the variable lambda is holomorphic, and with respect to the variable C is just an injection. Okay? And here we have a set, and if we vary the lambdas, we have deformations of this. Okay? These are deformations of the set. This is a holomorphic motion. Okay? Well, there are two results in this theory of holomorphic motions. Well, really there are just one result. One is the weaker version, okay? And this is the lambda lemma. The lambda lemma says that we can extend an holomorphic motion. And we can extend to the boundary of the set. Okay? If we have a holomorphic motion of a set, then we have a unique extension to the closure of the set. Okay? And there is a stronger version that we even can extend the holomorphic motion to a holomorphic motion of the ambient space. Okay? Recall that E was a subset of the complex of the Riemann sphere. And in this strong form of the lambda lemma, we can extend the holomorphic motion to a holomorphic motion of the full sphere. Not just E, but the full sphere. Okay? But these extensions are not just simple extensions. The extensions satisfy one extra regularity condition, that is the condition of quasi-conformality. Okay? So I have to talk about quasi-conformal mappings. But there is little time. I'm going, and I'll try to get faster. Okay. Well, what is quasi-conformal? What is a quasi-conformal map? The quasi-conformality is a a regularity condition for a function, okay? And it's a very desirable regularity condition because it is more flexible than conformality, but not so flexible, okay? But yes, it's more flexible. But it's enoughly flexible that it permits us to preserve certain features of conformal maps. Okay? Well, recall that a conformal map preserves shapes. Okay? This is the basic feature of conformal maps. They preserve shapes, angles. Okay? Well, a quasi-conformal map deforms shapes. But the deformation is, or we have certain control over the deformation. Okay? We can say that a quasi-conformal map is a map that deforms shapes, but this deformation is controlled. Okay? Obviously, we have to explain what is this control that we have over the deformation. Well, okay. We begin in a simple way, okay? Linear for linear maps, okay? For linear maps, recall this is very simple, okay? Any linear map from R2 to R2, we can define it as a map in complex variables like this. Okay, you can use this basic isomorphism. Okay, and we have this map. You can see it like this. Okay, well, we're going to do this. Okay, we have here R2, R2. Okay, and here is the linear map. Okay, and in the image we have a radius 1 circle. Okay, and okay, I will make a better picture. Okay, now what is the inverse map? The inverse of this circle is an ellipse. Okay, so you see that linear maps deform shapes. Okay, a circle is deformed into an ellipse. Okay, and we try to measure this deformation, and we measure it thanks to the Beltrami coefficient. Okay, if this linear map is AC plus B, the conjugate of C, then the Beltrami coefficient of this linear map is just the division of B and A. Okay. Well, there is also another measure, that is the dilatation. Okay, that is just the division of major axis and minor axis. Okay. Okay. How can we interpret this? We can see it like this. The linear maps deform ellipses into circles, as we see here. Okay. And see that if the dilatation equals 1, this means that the Beltrami coefficient, using this formula is valid for the dilatation. If the dilatation is 1, what this means? That major axis equals minor axis. And if these are equal, then the ellipse is just a circle. Okay? So if the dilatation is 1, there is no deformation because circles, and here we have also a circle, no deformation. Okay? But if the dilatation is 1, this means that the Beltrami coefficient is 0. No? Is 0. So Beltrami coefficient equals 0 means no deformation. Okay? Well, now recall here that this linear map I put it another, okay, T is like this, okay? Well, what is the partial derivative of T with respect to C is A, and the partial derivative with respect to the conjugate of C is B. The Beltrami coefficient, by definition, is this. Okay? So this is the division of partial derivatives. Recall that Beltrami coefficient equals 0 if and only if no deformation. Okay? No deformation. So what this means, no deformation? This means partial derivative with respect to the conjugation of C is 0. Okay? Well, this is quasi-conformal map, but at the most basic level. Okay? Now we can take these notions to subsets of the plane, and then also we can take this to Riemann surfaces. Okay? What I gave here was the basic definition. Okay? The basic definition. And this works for the R2, okay? And how we take it to subsets of the plane, we take it through the almost complex structures. Well, I don't. I think I don't have much time. Alex, ¿cuánto tiempo más puedes darme? Ok, listo. Ya, gracias. Okay, well, I'm going to explain how to do this. Okay, well, we have a parallel between R2 and the complex plane thanks to this linear isomorphism. Okay, but this is an isomorphism of vector spaces, of real vector spaces. Okay, but we need to define a complex multiplication if we want to complexify the space R2. Okay? A complex structure in R2 will permit us to define a complex multiplication in R2. Okay? The standard complex structure defines the usual complex multiplication. That is the complex multiplication that all of we know that works for the complex plane. Okay? But maybe there are another ways of perform a complex multiplication. Okay? Any linear map can be used to define a complex multiplication. Okay? This is like this. We have an element of R2, okay? And here we are defining a multiplication by a complex scalar, okay? And this multiplication is defined like this. The real part of the scalar, of the complex scalar, that is a real number multiplied by C, plus the imaginary part multiplied by this GC. What is G? G is this this combination of maps, okay, with M being the multiplication by E, by Y, okay? So this is the complex structure associated to this linear map. Okay, this linear map permits us to define this complex multiplication. Well, this linear map G, okay, is such that G squared equals minus the identity. Okay. So, what this means? A linear map, okay, a linear map define a complex multiplication or a complex structure on R2. Okay, but before here, we have seen that any linear map defines an ellipse, a Beltrami coefficient, and a dilatation. Okay, but this defines a Beltrami coefficient. Okay, mostly is a Beltrami coefficient. So really, a Beltrami coefficient can be used to define a linear map. Okay, with a Beltrami coefficient, you can define a linear map, and this linear map defines a complex multiplication. So if you take a Beltrami coefficient, you can define a linear map, and this linear map can define a complex structure. So with a Beltrami coefficient, you can define a complex structure. But recall that any Beltrami coefficient is associated with an ellipse. So also an ellipse can define a complex structure. Okay? This is very simple. Now, what we understand by for an almost complex structure, okay, we take an open set of the plane, a domain of the plane, and for this open set, we have tangent spaces, and recall that tangent spaces, in this case, are just copies of R2. So, what we do? We define a family of ellipses over these spaces, over the tangent space. And this family of ellipses will define complex structures in the tangent space. Okay? So an almost complex structure is a measurable field of infinitesimal ellipses in the tangent bond. What this means? This means that for almost all points in the domain, we choose an ellipse on the tangent space, okay? And the choosing of an ellipse is made such that the map that takes the point to the Beltrami coefficient must be Lebesgue measurable. I will explain this. Okay, we have here a subset of the plane. We all know that for a point here, we have a tangent space, okay, and this tangent space is R2. Okay, well, what we define in this tangent space, we define an ellipse. Okay, this ellipse has a Beltrami coefficient. Okay, this is the point U, and this is the Beltrami coefficient of the point U. And this Beltrami coefficient defines a linear map, and this linear map defines a complex structure. This complex structure is the complex structure of this tangent space. Okay? And that is this. This function is measurable. Okay? This function is measurable. This is an almost complex structure. Okay? Well, now we define quasi-conformal maps in subsets of the plane. Okay? And there are several definitions of quasi-conformal maps for subsets of the plane. Okay? I'm going to present just 3 of them. There is no time to present all of them, but just I'm going to present one of them, that is the analytical definition, okay? And the analytical definition of quasi-conformal maps is like this, okay? We say a map is K quasi-conformal if these 2 conditions hold, okay? First, the partial derivatives exist, but only as distributional derivatives, okay? And they are locally integrable, okay, in L2. And we have this condition for the distributional derivatives, okay? And this condition satisfied in L2, okay? And this constant K is this big K, in this form, okay? And in this case, the Beltrami coefficient of this map is the division of both distributional derivatives. Okay? So this is the analytical definition of quasi-conformal maps. There is 2 other definitions that are geometric definitions. Okay? Maybe this is not so clear, or maybe when I talk about quasi-conformal maps, I said that quasi-conformality is essentially a deformed a controlled deformation. And maybe with this condition, we can see where is that controlled deformation. But maybe we can understand it with the geometric definitions. Okay. Well, there are two geometric definitions. One is with quadrilaterals, and the other one is with animals. Okay, and both definitions must be understood in relation with the modulus of a quadrilateral or the modulus of an animus. Okay, what if a mapping is quasi-conformal? We understand that it changes the modulus of quadrilaterals, but this changing is bounded. Okay, it's more or less like this. Okay, and the same is for the annulus. Okay, there is a deformation. There are several properties for quasi-conformal maps, but there is no time to talk about this. Okay, but I get here. Okay, recall the lambda lemma, and the full version of the lambda lemma is like this. I have a holomorphic motion of a set, and this holomorphic motion has a unique extension to a holomorphic motion of the recall we extend the holomorphic motion of E to a holomorphic motion of the Riemann sphere. Okay, and this extension, okay, this extension to the full Riemann sphere is a quasi-conformal endomorphism of the Riemann sphere. Well, there is no time for more, but the result of Magnez-Adam-Sullivan says that recall that we have structurally stable rational maps, okay? And the result of Magnez-Adam-Sullivan is that the set of these structurally stable parameters is open and dense in X, okay? And also that hyperbolic maps are structurally stable. Okay, indeed, they form an open and closed set of the structurally stable parameters. Okay, so the conjecture of the density of hyperbolic maps is just to prove that any structurally stable map is also hyperbolic. Okay. Okay, well, this is it. There are several things that I couldn't say, but well, here it is for today. Okay.
Okay. So we thanks a lot to Alberto Castillo by his presentation. And is there any question for him about his presentation? Also, you can write it down, any question in the Zoom chat, please. Well, is there no questions? Let's thanks again, Alberto Castillo.
Thank you.
Okay, very good. So we're gonna make a break and we are gonna continue with our seminars in 10 minutes more. Very good. So we are going to continue with our seminar, and our next speaker, is going to be Professor Linda Keen. Okay, so let me say some things about her before she starts. She has been a professor in the Department of Mathematics and Computer Science in Lehman College of the City University of New York, and a professor of mathematics at the Graduate Center of the City University of New York. She's an excellent mathematician. She has worked in very special places like Berkeley, Columbia University, Boston University, Princeton, and the MIT. And she has some contributions about Riemann surfaces, hyperbolic geometry, Kleinian groups, and Fuchsian groups, complex analysis, and hyperbolic dynamics. Okay, so we're gonna give a time to Professor Linda Keen, and she's gonna talk about meromorphic functions with two asymptotic values. So it's your time, Professor Linda. Thank you.
Okay, well, thank you very much. It's a pleasure to be able to talk to all of you scattered so far away. What you've been talking about, what we've been hearing about now often are rational maps. And so let me just review a little bit what we know about rational maps now. They're finite, holomorphic, branched, finite to one, branched holomorphic coverings of the Riemann sphere. And the orbits of the critical values, that is the images of the branch points, determine the behavior of the orbits of all of the other points in the plane under iteration. So the dynamic plane is separated into regions where the behavior is stable or predictable, and it's by a set where it's not stable. So oops, this is not coming out the way I had expected. All right. So rational maps are finite. So as we vary the critical values, this bifurcation into stable and unstable behavior can change. Oops, let me see if I can make this work better. Okay, that's better. Can you see this now?
Yes.
Whoops. Okay. All right, so the first example with rational maps are quadratic maps. And there we see the very familiar picture of the dynamic plane for z squared plus c with c equal to -1, where the critical point, 0, is periodic. It goes from 0 to -1 and back again. Everything in the white region is attracted to that periodic cycle, and everything outside in the orange, yellow region goes off to infinity. The Mandelbrot set measures what happens to those functions z squared plus c by looking at the orbits of c. In this black region, the orbits stay bounded, and out here, c goes to infinity under iteration. So we have only predictable behavior that everything except some Cantor set goes to infinity. Now, we find Mandelbrot sets or Mandelbrot-like sets in other rational map families. So the rational map that is a degree 2 map can be written, and fixes infinity can be written as 1 over rho times z plus 1 over z plus b. And rho is the multiplier at infinity. So if we take rho less than 1, then infinity will attract at least one of the critical values. This rational map has 2 critical values. In the green region, it attracts both critical values. And in each of these Mandelbrot-like regions, one critical value goes to infinity and the other stays bounded. And if I blew these up, they would look just like a Mandelbrot set. Another family that we've seen is cubics, where 0 is one critical value, but A is another critical value. And in this region, in this green region out here, the iterates of A go to infinity. In this purple region, the iterates of A tend to 0. And then we see we have Mandelbrot-like regions here, where the iterates of A tend to stay bounded away from 0 or infinity, and inside tend to periodic cycles. Okay, so what happens if we think about a transcendental map? A transcendental map is not finite to 1, but infinite to 1, and it's holomorphic. And it has an essential singularity at infinity. So for a rational map, we can define f at infinity. But for a transcendental map, f is not defined at infinity. So how does this affect the dynamics? And what happens as we perturb these dynamical systems? So today I want to look at parameter spaces of the simple family of transcendental maps, where we can see both the similarities with rational maps and the differences with rational maps. And what I talk about represents various joint projects that I've carried on over recent years with Tao Chen, Nuria Fajella, and Yunping Jie. So what are the new ingredients? That f of infinity is not defined, but that also means when we iterate, if we take a point whose iterate goes to infinity, then we can only take a finite number of iterates before the iteration is not defined anymore. And so we have a whole set of points that are prepoles of order n for every n. They are basically essential singularities of the nth iterate. And so we can say infinity is a prepole of order 0. Poles are prepoles of order 1, and then if n is bigger than 1, we have a prepole of order n satisfying this condition. Okay, now another difference is that we know that for rational maps, the only kind of singular values we can have are critical values, that is the images of the branch points, which are where the map is not a local homeomorphism. But for transcendental maps, we can have another kind of singularity called an asymptotic value. And that's defined as follows. We start with a path that tends to infinity. And then we look at the image of that path under our map F. And if that the image of the path has a limit point as we go out to infinity, A is called an asymptotic value of F. And the example to think about is the exponential map, where if we parameterize, for example, the negative real axis, then as we go out to minus infinity, and we take E of that path, we get a path that ends at 0. So 0 is omitted, but this limit does exist, and we call this an asymptotic value. So that's an example of a locally omitted value where we take a neighborhood of this asymptotic value. We look at all the pre-images, and then we see how F maps any one of the connected components of the pre-images back onto U minus A. We ask, is this a local homeomorphism? So the case of e to the z, where we have 0 as an asymptotic value, is a case where the asymptotic value is isolated. And an asymptotic value that's isolated is locally omitted and called logarithmic. And those are the only kind we want to talk about today, so I don't want to get into more complicated things. Okay, so the dynamic behavior, look, when we start talking about it, looks much as what we have for rational maps. So we start with, if we have a periodic cycle of points, that is a set of points where f maps z0 to z1, z1 to z2, and so on, and finally zn minus 1 back to z0. This is our periodic cycle. Since the function's holomorphic, we look at its derivative, and the derivative going around the cycle is the same at each point, and that's the multiplier of the cycle. Now we say a point, not necessarily a periodic point, is stable or predictable if there is some neighborhood of that point so that the iterates of that neighborhood are bounded in the spherical metric, or equivalently that the iterates form a normal family on this neighborhood. So clearly, since infinity and the prepoles can't be iterated infinitely often, they can't be stable. But the stable points form the Fatu set, and the complement of the Fatu set is the unstable set, or the Julia set. And the infinity and the prepoles all belong to the Julia set. Okay, so the Fatu set is open, it might be empty. The Julia set is closed by definition, it's never empty. And as for rational maps, it's a closure of the repelling periodic points. Those periodic points where the multiplier is bigger than 1 in absolute value. But it's also the closure of the prepoles. So the prepoles are dense in the Julia set. This was proved by Baker, Cotis, and New, 1991. Okay, so both sets are completely invariant as long as we take into account the fact that there are points in the Julia set whose iterates are not defined. And as for rational maps, well, for rational maps, we know conjugation by a Mobius transformation doesn't change the dynamics. In this case, we will only conjugate by linear maps because we want to keep a point at infinity as our sense of singularity. If we take a Mobius transformation, it's going to move infinity, and so it will move the essential singularity, and it's much easier to keep it at infinity. So we'll conjugate by linear maps, or not out by conjugation, linear maps. Okay, now, as we've seen for rational maps, we can classify the Fatu domains, and we have similar classification for transcendental maps. If we start with a component of the Fatu set, then we look at iterates of this component. If for some m and n, the image of this component under the nth iterate is contained in the image, or equal generally to the image under the mth iterate, then we say that D is eventually periodic. And the reason that we have to worry about contained in is because of these locally omitted values. If the iterates of this domain D never intersect, then D is called a wandering domain. And cycles of stable domains, so eventually periodic domains, are called attracting or super-attracting if the cycle contains an attracting or super-attracting cycle. It's interior, and that happens when the multiplier has less than 1 in absolute value. Super-attracting, the multiplier is equal to 1. Parabolic, if we have a parabolic periodic cycle on the boundary of the Fatu domains, the cycle, and then the multiplier is a rational multiple of pi. We can also have rotation domains. In that case, the iterate that maps the domain to itself is holomorphically conjugate to a rotation map on that domain. And multiplier is either the 2 pi I theta, and there are conditions on theta, it's irrational, but, for which a rotation domain can exist. Now, what we can have for transcendental maps are essentially parabolic or Baker domains. And we have such a domain if there is some point on the boundary of the domain, so that if we take the iterate of any point in the domain under an iterate that fixes the domain, then the limit of the iterates in that domain tend to this point on the boundary. Now, if this point on the boundary is finite and the function is well defined there, that's when we have a parabolic. But if this point is infinity, which it can be, or a non-parabolic point, like a prepole or something, then we can have a Baker domain. So the singular set is the union of all the singular values of F, and it consists of critical values, asymptotic values, and then if we have infinitely many, these can have limits. And the post-singular set is the closure of the iterates of all singular values plus infinity. Okay, and the theorem says that if we have attracting, super attracting, parabolic, or a Baker cycle of Fatu domains, then we must have a singular value inside one of the domains in that attracting basin. And if we have a rotation domain, then the boundary of the rotation domain contains the omega limit set of the orbit of a singular value. Okay, now Sullivan showed that rational maps can't have wandering domains, and so that means that we can use the critical values to see what the dynamics are for any rational map. After various people who looked at entire maps, Baker, Cotis, and Liu proved in '92 that a transcendental map, which has a finite set of singular values, that is finitely many critical values and finitely many asymptotic values, cannot have a wandering domain. And functions with finitely many singular values are called functions of type finite type. And their dynamics are controlled by the singular values, so they live in finite dimensional families. And so this is a nice set of functions to begin to look at when we want to see what happens with transcendental functions. And just as for rational maps, special maps that, or they're not so special, in fact, they're pretty generic maps that we can perturb where we don't change the quality of the dynamics and get what we call hyperbolic maps because they're expansive on the Julius set. Equivalently, for rational maps, the post-singular set is destroyed from the Julius set. For transcendental functions, it makes more sense to use this as the definition of hyperbola. Okay. Now, since we want to understand how having asymptotic values affects the dynamics of the transcendental functions and their parameter spaces, today I want to look at functions that don't have any critical values. They only have asymptotic values. And such a function has to have at least two asymptotic values, can't just have one. And in fact, functions with exactly two asymptotic values, the exponential is 1, but it has asymptotic values at infinity and 0. And so if we take a Mobius transformation of such a function, it will have two asymptotic values in the finite plane, or unless we take a linear. And one could write this as a to the z plus, or a to the 2z plus b, c to the 2z plus d, but it turns out that it's nicer to write this in a more symmetric way somehow. Here, the asymptotic tract, the region that contains these asymptotic paths whose images go to the asymptotic value for the exponential, are the right and the left half planes. So we see that there are two asymptotic tracts. The asymptotic tract for the left half plane is B over D, and the asymptotic tract for the right half plane is A over C. Okay, now, when an asymptotic value is infinity or a pole or a prepole, then it's playing a role in the dynamical system, both as an essential singularity and as an asymptotic value. So since what we want to understand first is how asymptotic values are affecting dynamics, we want to look at families that we call purely meromorphic functions, where no asymptotic value is an essential singularity. So we don't want to look at the exponential. We want these functions with two asymptotic values to actually take 0 infinity to two finite values. Okay. And so one of the nice things about purely meromorphic functions that I proved with Bob Devaney is that purely meromorphic function can't have Baker domains. So that even cuts down what we know about the possibility for the dynamics of these functions. So the first family that we can look at where we have two asymptotic values is the tangent family. And it's more convenient to write the hyperbolic tangent, but that's really, from our point of view, the same as the tangent family, because multiplication by I conjugates lambda tangent z to lambda hyperbolic tangent zeta. Okay. So the asymptotic values are, let's see, I think I skipped. Okay, so a little history. The tangent family was first studied in the 80s by Devaney and with me, and then I did some more work with Devaney in the 90s and with Yanina Kotas and my student W.H. Zhang and some others. And then more recently, Tao Chen and Yunping Zhang and I proved some results about renormalization in the tangent family that seem to be generic for families like this. Okay, so what happens for this tangent family? The asymptotic values are plus and minus lambda, and they behave symmetrically. So that means that if the iterative lambda does something like tend to a periodic cycle, the iterative minus lambda also tends to a periodic cycle. If lambda, lambda can't be a fixed point, but it could land on a periodic cycle, and then minus lambda does the same thing. There are no super attracting cycles because the derivative is never 0. And if there is an attracting periodic cycle, it has to attract lambda. So it has to be, if it attracts exactly one asymptotic value, the other asymptotic value has to go to another attractive cycle of the same period and the cycles are symmetric. The other possibility is that both asymptotic values are attracted to the same periodic cycle, and so then that cycle has to have even period. Okay, so if we have an attractive periodic cycle, or if the asymptotic cycle values are attracted to a periodic cycle, then the function is hyperbolic or parabolic. Otherwise, both asymptotic values have to be in the Julia set. So here's a picture of the tangent space parameter plane. So this is the lambda plane for tangent or hyperbolic tangent. And it's colored as follows. Yellow means we have period 1. Cyan means we have period 2. Red means we have period 3. I think you can see these red domains here. This kind of olive green is period 4. And there's some more period 4 ones along here. Bright green, these bright green little dots are period 5. And these dark blue regions are period 6. Okay. And now let's talk about these regions in the parameter plane. So first of all, let's look at what we can do with the multiplier map. So if we have a periodic cycle, the multiplier map defines a holomorphic universal covering map of this domain onto the punctured disk. Omega p in this case is one of these domains. And this multiplier map is either an isomorphism onto the punctured disk, and of course, lambda can't be 0, and that's why it's the punctured disk. Or this domain is simply connected and isomorphic to a half plane. So, and in that case, there's a unique point on the boundary, which we call the virtual center, such that if we take any sequence of points in the domain tending to that point, the limit of the multipliers is 0. And, you know, in the Mandelbrot set, the center of a component is where the derivative is 0. Here we have a virtual center. It's not in the component, but on the boundary. And we can't really have the cycle there, but the limit of the multipliers can exist. Okay. What happens there is that the p minus first iterate is infinity. And we call this virtual center, another name for it that we can use for the tangent is a virtual cycle parameter. This condition we can define independent of being in or on the boundary of a hyperbolic domain. We look at parameters that eventually land on where the asymptotic value eventually lands on infinity. But we call it a virtual cycle parameter because if we look at these iterates, lambda star, then we take the first iterate and the second iterate, we get to the p minus second iterate, and then we get to infinity. And we can't iterate. But if we take an asymptotic path and we look at the limit of the p iterate along this asymptotic path, on the point we started with. And so we call this a virtual cycle. So in our picture here, here's our disk minus the point. And then here are these other simply connected components. Here we have 2 cycles of period 1, 2 cycles with fixed points, each attracting one of the asymptotic values. And here there's 1 cycle with a period 2, 1 period 2 cycle that attacks both asymptotic values. Now let's look in here. I should have a blow up of this, but I don't today. Here we have two cycles, each of which is period 2. And in this domain underneath, or maybe it's easier to look here. Here there are two cycles of period 2. This domain under here has one cycle of period 4 that attracts both asymptotic values. And this point where these two domains meet is a pole of the tangent. So this is 3 pi I, this one is pi I. And what happens here is that the multiplier as we come down to here goes to 0. The multiplier as we go up to here goes to 0. And these two components meet at the center. Now, along components here, we have standard parabolic bifurcation. You can see we have a period 2, a period 3, 4, 5, and so on, all the way down to this cusp. But now if we look at this period 3, we see it has a center and then a period 6 component that's attached to it. So it's a very similar situation to this. And that's the story in the whole parameter plane for these components. Now, the disk is the analog of the outside of the Mandelbrot set because both asymptotic values are attracted to the origin. And there, the Julia, for lambda in the disk, the Julia set of the tangent is a Cantor set. And if we look at the map on the Julia set, it's conjugate to a shift map on an infinite set of symbols. So we have to define, we define an alphabet that contains finite and infinitely many, contains infinitely many elements, but we make sequences out of finite or infinite sets of symbols in that sequence, and we can define the shift map on that set of symbols where it's not defined if we run off the end of the finite one. And then we can show that T lambda is conjugate. Okay, and in this region, in D, we can define the analog of external rays by using the multiplier map. There will be rays that will be invariant. So we get standard bifurcation at the ends of those rays. The other hyperbolic components are more like the components in the Mandelbrot set where the asymptotic values tend to non-periodic cycle. Okay, and the coloring was by the cycle of the period and not whether we had 1 or 2. Okay, so for the tangent map, it wasn't quite so hard to prove that every virtual center parameter is every virtual cycle parameter, it should say, is a virtual center and vice versa. The simply connected components come in pairs and share a virtual center that we saw. And in one of them, we have these two separate cycles of period P, and the other, there's the single cycle of period 2P. So we think, in fact, we think that the cycles merge or split center. And if we take the virtual center and we look at that virtual cycle, and then we label the inverse branches, we can go back around from infinity back to the asymptotic value. That gives us a sequence of inverse branches, and we can use those to give a label to each of these components that are not the disk, each of these hyperbolic components. And that's analogous to coding the components of the Mandelbrot set, the hyperbolic components, by what happens at the center, the cycle for the critical value. Okay, and in fact, a few years ago, Tao Chanyan, Ping Zhang, and I showed that this is a rather general kind of phenomenon. We showed that as we go up the imaginary axis in the tangent plane, there's an interleaved pair of sequences so that we have period doubling at 1, and then at the next point we get a virtual center and we have period merging. And these sequences have a common limit, and at that limit point, the tangent map for that limit point, the orbits of the asymptotic values are attracted to a Cantor set. So this is a renormalization, and the proof involves using holomorphic motions, but it can be used more generally than just for this tangent map. But let's go back and look and see what it says here. So it says that what happens is that when we're in a component here with period 4, and we have both asymptotic values tending to the cycle, we have 2 asymptotic tracks and 1 asymptotic, so each corresponding to one of the asymptotic values. And when we're in here, the asymptotic value goes from in forward iteration, from one asymptotic tract into the region and then back again. And when we go here, the asymptotic value, one of the asymptotic values moves through the tract so that we now have separate tracks, a track corresponding to each of the cycles. So we have these cycles split actually as we go here. And now we have standard period doubling to period 4, and now the cycles merge as we go to period 8. And then we get period 16 and the cycles split. So we keep going, splitting and merging, and somewhere in this region, way in here, is that point which is a limit of all of these points. Okay, so let's move on now to another family with 2 finite asymptotic values where they're not symmetric anymore. So here's our general form, and using our linear conjugation, we can fix the origin by letting A equal minus B. Then if we call the multiplier at the origin rho, and we denote the 2 asymptotic values, A over C and B over 2 by mu, we can call this family of functions of the form f lambda rho, because the 2 asymptotic values satisfy this nice condition with respect to this multiplier. And we get this formula that exhibits the 2 asymptotic values symmetrically, but really depends on lambda and rho. And if we fix the way we did for the rational maps of degree 2, RAD2, the multiplier to be less than, and we vary lambda, we get a one-dimensional slice in this family, which I'll probably in the rest of the talk will continue to call F2. Okay, so if we want to study the dynamics, we follow the asymptotic values. Like RAD2, at least one asymptotic value is attracted by the fixed point at the origin, since it's attractive. And we denote the immediate basin of the origin by A naught. Now, if both asymptotic values are in A0, then A0 is completely invariant, and the Julia set is a Cantor set. And as we did for the tangent map, we can use inverse branches to label the Julia set with finite or infinite sequences. And F is conjugate to the shift on the sequence space. On the other hand, if there's only one asymptotic value in A0, then A0 is simply connected, and the other asymptotic value either tends to an attracting or parabolic periodic cycle, or there is a Siegel disk and rotation domain, and the asymptotic value belongs to the Julia set, or the asymptotic value lands on a periodic cycle in the Julia set. In any event, the asymptotic value can't be in the Fad2 set unless we have an attracting or parabolic periodic cycle. Okay, so let's look at this plane. So now, as I said, F2 is this slice. We fix rho, and we get a natural division into 3 sets. And we define them as follows, and I'll show you some pictures in a minute. In S, the iterates of both asymptotic values tend to the origin, and that's called the shift locus, and it's like the exterior of the Mandelbrot set. Then in MU, the asymptotic value of lambda goes to 0, and the iterates of the asymptotic value mu don't. In M lambda, the roles of lambda and mu are reversed. So mu is attracted to 0 and lambda isn't. And these each contain hyperbolic components in which the functions are topologically conjugate, and the period of the attracting cycle is P. That's the P and the omega P. So here's the picture. And so this green region is S. That's where both asymptotic values go to 0. Is where lambda goes to a fixed point and mu goes to 0. And in fact, somewhere along this nice real line of symmetry, we have a map that's conjugate to tangent map. Then we have standard bifurcation along here. Period 3, 4, 5, and so on. We have cusps. And here we have a period 2 component. Here we have outside. Here we have period 3 components that we see. And here we see a little yellow dot. Now that yellow dot is actually has a lot going on there. So this region over here is where lambda is tending to these components, are where lambda is going to an attractive cycle, but somewhere in here is where mu is going to an attractive cycle. So let's blow that up. And we see that we get a very similar picture. It looks like we've inverted the other picture in a circle. And here again, here is 0 because lambda can't be 0. Functions aren't defined, because then mu is infinity and we are no longer purely meromorphic. But here we again have our period 2 and period 3, 4, 5, 6, 7, 8, 9, 10, and so on, all these periods that we can see around here. And what happens around these components that are attached to this big component here? Well, we see a lot of, and one of the questions we want to ask, how can we describe this? Well, it turns out that these components are actually components like the ones we saw on the tangent map. So here we have the asymptotic value lambda going to a period 2 cycle, and the multiplier varies as we go in here. This is like a half plane, the way it was for the tangent. And as we head out to this point on the boundary where all of these bifurcations are accumulating, the multiplier is going to go to 0. A virtual center. And as we move through here, the asymptotic value lambda will go from being, it will move through the asymptotic tract, and we will have an exchange going on. And out here now, it gets attracted to the other, to the same cycle as mu. So, okay. So these components that exist for this family, and in fact for more general families of purely meromorphic functions or even meromorphic functions, are described carefully in a paper that I wrote with Nuri Fagella, and then for another family of functions that I wrote with Tao Chen. And they have properties similar to the shell components for the tangent family. So as I said in the picture, the multiplier map is a holomorphic universal covering that extends continuously to the boundary. It is analytic and has cusps at the inverse images of 1. And it contains this unique boundary point, the virtual center, which is in fact a virtual cycle parameter. And what's true for this family and for somewhat more general families, but not necessarily for all purely meromorphic functions, every virtual cycle parameter is a virtual center and vice versa. So it's possible that in more general families, virtual cycle parameters live somewhere in the bifurcation set, and they're not on the boundary as accessible points of hyperbolic components. But let's look at the shift locus S, because we want to understand that better. And so if we're in this shift locus, the entire Fatou set consists of the immediate basin of origin. And if we linearize with Poincare linearization, we get a map from a domain around 0 into the plane where we conjugate our map to multiplication by rho, the multiplier at 0. And in the notation, we take O lambda as the largest neighborhood where this map phi lambda is injected. But we can pull it back to pre-images of O lambda by analytic continuation. So we have to use different branches of the inverse to pull it back, and we'll see some pictures of that in a little bit. And somehow the number of inverses that we take before we find lambda is the analog of the escape function for polynomials. So to understand the shift locus for the Mandelbrot set, we needed to look at external rays. And here we don't have external rays, but we're going to have to do something that kind of makes up for that. And one of the things about the external rays is to understand escape rates and so on. And here we'll need to do something different, but we'll have to, but the escape rate does talk about how fast the point gets iterated to infinity. So here somehow we want to see how fast the asymptotic value lambda goes to 0. So, but we have this duality between lambda and mu. So we separate our two sets, one where mu is the closest asymptotic value, it lives on the boundary of lambda, and lambda is outside. And then we use a 0 to denote the interior of that set. And then similarly for mu, the opposite. And we can show that there's an inversion from this set to this set, given by sending lambda to minus mu, that leaves some curve, which is the boundary of the common boundary of these two sets invariant? Well, that common boundary is missing a point because we can't have lambda equal to mu. So on the common boundary, both lambda and mu are in the boundary of this set, but they can never coincide. Okay. So there's a conformal homeomorphism. This is of this S lambda naught onto C, the plane minus an annulus, which extends continuously to the invariant curve minus this point that we can't put on there. And since we can do this for both S lambda naught and S mu naught, we can put the two maps together and conclude that S is conformally isomorphic to the punctured plane minus this one point. So what that says is that, like the shift locus for quadratics and rationals, there are no islands of hyperbolic components. So it means that this picture actually gets filled in. We can't get around any one of these things. These things are all connected. Even these guys over here move into here. So this green region is simply connected. Its discontinuity is way far away from anything that's near these hyperbolic components. And so it's very complicated as we go into the boundary here. Okay, so what are the ideas? I certainly don't have time to carry out the full proof, but what are the ideas and the proof of that theorem? The proof, first of all, we use a construction which I had used with Lisa Goldberg for RAT2 of a model map. I'm trying to model the parameter space with the dynamic space of a given map. And then I need to use Teichmuller theory for the twice punctured torus to somehow get control of escape rates. So how do we do this? I take Q in F2 with a non-zero fixed point and multiplier rho, and I assume Q naught attracts lambda naught. I can do this by taking, for example, this linear conjugate of the tangent map, so I know, in fact, the Julia set is just the imaginary line. And then I can use the attracting, so we have two attracting basins for Q, one of Q naught and the other for 0. And then I use the attracting basin of Q naught as the model. So here is the model. And I have an inverse Poincaré linearization map defined for this model. I can linearize at Q naught as well as 0. Okay, and so now on the one hand, I have the basin for some lambda in my shift locus, and I have my linearization there, and the map, as I go down to the disk, takes me to the origin and to the conjugation of multiplication by rho. When I uniformize the model map, I get a similar thing. I can go from to this disk where I conjugate to multiplication by rho. So if I go first from going around 0 in A naught to the disk and then back to K naught, I get a map, and then I extend this, take the appropriate extension, I get a map that takes me from A naught into K naught. And I can look at the image of lambda in K0 under this map, and that's my map E. And that's a nice holomorphic map. So basically, we're going from our map here, we go around 0, and it maps around here, and then we can pull back this disk around 0, and we pull back, and we get a bunch of regions, and then we can pull these regions back. A0 pulls back to A1, and these other pre-images of this disk pull back to regions around in here, and so on. And so I can see where the image of lambda over here lands, and it lands somewhere in this combinatorial description of this model space by these pullbacks of disks around here. Okay, and the hard part is the inverse map. So the inverse map, I want to start with this model. I want to pick some point in here. And then I want to construct from that point a map in S lambda in the shift locus. So to do that, I have an asymptotic value here, lambda naught, and I take a point here. And now I topologically construct a covering map. And now I apply Q and pull back. And then I continue to do this inductively. I pull back by taking this pullback map. I pull out pre-images that aren't defined of that, and I construct a sequence of covering maps and take a direct limit of these maps. I mean, it's a complicated construction that I can't possibly explain in the amount of time I have today, but that's the idea. So I get this direct limit map, and this direct limit map gives me some domain H infinity, which is topologically equivalent to the plane minus Cantor set, and it has these points whose orbits are like those of the asymptotic values. So I have something that topologically looks like the map it should be. And then I have to use quasi-conformal surgery techniques to construct a holomorphic map from there into this A lambda. And so I can do this to get it into some A lambda, and then I can modify that to make sure that the map is holomorphic and get it to a particular lambda. But one of the problems in doing this is to use the fact that the other asymptotic value is somehow backward in these pullbacks by a certain number of pullbacks. So it is not only where it is in one of these regions, but how many regions back. And that's kind of like the escape route. And in order to do that, I have to use something about the mapping class group of the twice punctured torus on its Teichmüller space, and then understanding how finding the right element of the mapping class group is the key. And that's like measuring the escape rate. Okay. Well, I am using a lot of your time. The boundary. So we saw in that picture that the boundary is pretty complicated. Now we know that the virtual cycle parameters are virtual centers of shell components, and they belong to the boundary of M. So here are the virtual centers, and they belong to the boundary of M, because these components are in M. And we know that the points where F has a parabolic cycle are also on the boundary of the hyperbolic components in M lambda. But the point is that they're all also on the boundary of the shift locus. And so Chao Chen and Yunping Zhang and I proved that the virtual center cycle parameters and the parabolic parameters. They belong to the boundary of the shift locus. In fact, they're dense in the boundary of the shift locus. And this map extends continuously to them. In fact, they're even accessible from inside the shift locus. So that means we take sequences of points inside the shift locus tending to these points on the boundary. Then those sequences have to have unique limits, and those limits are these virtual cycle and parabolic parameters. Okay, so in order to prove this, we need an analog of the external rays, and then we have to show that they land. And so what we do is use that model and define a combinatorial tree in that model with ends in the Julia set. And then we pull back that model. We identify the ends of the path in the tree with points in the Julia set using our identification with sequences. The finite paths end at prepoles and the repeating paths end at repelling periodic points. Then we pull this model that we have, the combinatorial tree, back to paths into S0 for a given A0, and then we show that the images have landing points. And that's really the hardest part. But I just wanted to give you an idea of what this tree structure looks like. So here we have a division of the model space into fundamental domains. So Q0 maps this path through the asymptotic value onto a curve inside and keeps mapping it inside. The pullbacks of these inside, this black circle maps back to a curve that has to hit infinity, and all of these images inside pull back to closed curves in here. Then they also pull back, this region also pulls back into, because periodicity, into infinitely many regions. This region between this circle through our asymptotic value, which in this picture got called T0, and the pullback into the asymptotic track gets pulled back to curves that go from infinity to the pole. And so we get these curves to the poles, and we can divide these regions up. And now these brown curves are pre-images of these red curves, and these black curves are pre-images of these black curves. And we draw a curve from a point that we start here to each of the poles, and then to the pullback of this point onto each of these curves. And then we pull this whole structure, this infinite structure, back to each of these pullbacks, and then back to each of these pullbacks. And so by coding the inverse images, we code these branches of the tree that go from one vertex to another, or from a vertex to a pole. And then we pull this whole structure back by that map E that takes us back to the shift locus. Okay, and we have to show that what we get converges, and there's certainly no way I can tell you that today. Remaining bit of time, and take just a few more minutes, I want to show you that there are other one-dimensional slices of that. For example, the exponential family. So we give up the idea that functions are purely meromorphic, and we allow one of the asymptotic values to be infinity. And now a whole bunch of people have worked on the exponential family. And I've written down a bunch of their names here, and I apologize to anybody whom I left out. But the picture that we get for the parameter space, and I take it in the form E sub A of Z equal E to the Z plus A, this fits in with the formula that I was using before and is actually an easier one to work with. We see that the parameter space for the exponential looks quite different. All of the components are unbounded. So here's our big period one component on the left. We have, excuse me, big period two components on the right, the cyan components. But also on the right, we have these red regions, and this brown stuff is round off. So these red regions really extend all the way back out to the right. So I have infinitely many period three components between every pair of period two components. And now if you look here, you see infinitely many period four components between every pair of period three components. Here it's period three components, and here are period four components, and they come down along here. And between the period four components, we have period five components, and they come all the way out here. So they come all the way out and they get skinnier and skinnier. And Schleicher and Rempe and Fagella and Devaney have coded what happens to these components all the way out here, and shown that that this structure is actually what's happening for the exponential. Okay. And they also show that the parameter plane contains a family of curves along which the asymptotic value escapes to infinity. The curves are indexed by a Cantor set, and so we call that set a Cantor bouquet. Okay, so here is yet another slice of this family. So there's still lots of questions. So if we assume that the asymptotic value mu is not infinity, but a pole, and in fact, so in this case, we took it as the pole 0, we get a picture that looks like this. And it's an interesting picture because aside from the fact that we look right to left, let's compare it with the purely meromorphic case. On the right, we have this big region here. And we have all these shell components off our main component here. On the other hand, on the left, we have a picture that looks like the exponential. We don't see period 4 components, but we see period 5 components. And again, this is round off error going in here. Between the period 5 components, there are period 7 components and period 9 components. Here's a blow up of that. Period 5, period 7, period 9, period 11, and so on. So we have all these odd components. So first of all, there aren't hyperbolic components. They look like hyperbolic components because they're measuring where the second asymptotic value is going to something attractive. But because the asymptotic value is a pole, the singular values live in, so all the 0 and all the images and pre-images in particular live in the Julia set. So it's certainly not hyperbolic, but we call these pseudo-hyperbolic. And we see the components, they're all bounded, except for the period 1, which has its virtual center, if you like, at infinity. And there are these exponential-like components of every odd period lining up in the left half plane. Now, if we look at a blow-up near this period 2 component, we see that something else is happening. here's the virtual center. And here's a virtual center of a period 4 component and a period 3 component. At this virtual center for the period 2 component, we have infinitely many components where we have period 4 coming in. So it's like the exponential picture, but pulled back to this virtual center. And then we have the period, so here's period 4, here's period 6, here's period 8. So from the period 2 component, shell component, we have all these, what Tao Chen and I, who've been working on this, like to call hybrid components, because on the one hand, they have a finite virtual center, but on the other hand, they're deployed like the exponential components. And they start at period 4, period. And so from period 2, we add 2 and 2 and 2 again, and we get all the periods, so all the even periods here. At period 3, we start with period 5 and then get 7, 9, and so on. 4, we get period 6 and 8 and what have you. So at the moment, Tao and I are trying to write down a complete description of this space and understand how exactly we are putting together this exponential behavior with this purely meromorphic behavior. Okay, I think I will stop there and say thank you to everybody. Okay. Okay.
Okay.
Let me get view so I can see some of you now. Okay.
Okay. Perfect. Very good. So let's thank Professor Linda Keen for her presentation. Okay. And now, is there any questions about the topic, about the presentation?
Yes. Hello. I haven't seen any Mandelbrot-like.
1 second. Let me make you bigger so I can see you better. Just have to change my view here.
I'm Alfredo.
You speak. Okay, that's good. Okay, good. Now talk.
I haven't seen any. Hello, long time no seen.
Yes, it's been quite a while.
I haven't seen any Mandelbrot-like components in neither of your pictures.
Have what?
I haven't seen any Mandelbrot-like components in any of your pictures or islands.
So we think of them, they're Mandelbrot-like in the sense that they fit together as hyperbolic components, but they don't form Mandelbrot sets. I mean, in the same way you get the kind of picture that you get. So they are the complementary kind of thing to what happens from the shift locus, and they contain hyperbolic components of all periods, and they can be coded combinatorially using the virtual centers, the way you can code the Mandelbrot, the hyperbolic components of the Mandelbrot set. And you can see how you can make trees that go from one into another. So in that sense, they are Mandelbrot-like. And the other thing is that they seem to be generic in this space, at least of with finitely many singular values. You see them, for example, if you look at lambda tangent to the p, z to the q. So that, again, looks like you throw in a critical value and you get some things that are a little bit like what you see in cubics, and quartics and so on, but you don't get the Mandelbrot picture because you don't have any critical values. Okay, I mean, the infinite, I think it's really the fact that it's infinite order, and the covering's infinite. So you get these components that you get here in these shell components are infinite to one coverings of the punctured disk. So in each of these components, you have infinitely many sort of fundamental domains where the multiplier takes values in the punctured disk. So it's different, but it is a generic kind of picture. I hope that answers a little bit. Any more questions?
Okay, so if there are no more questions, we will thank Professor Linda Keen again. Very good. So we're gonna make a break for lunch, and we're gonna see you at 2 p.m. Peruvian time zone, GMT -6.
Okay. Bye-bye, and thank you for your attention.
Ok, muy bien. Podemos comenzar entonces. Very good. So let's continue with the session of complex seminary with our seminars about complex dynamics. And it's a pleasure now to introduce Professor Rudy Rosas. He is professor of the Pontificia Universidad Católica del Perú. He did his PhD studies at IMPA in Brazil, and he has worked with singularity of holomorphic foliations, and also he has won the CAPES Award for the best thesis in Brazil in the year 2005. So we give you your time, Professor Rudy Rosas. Thank you.
Bueno, gracias. Antes que nada quiero felicitarnos por la iniciativa de organizar este evento, los alumnos que han participado en esto, y bueno, agradecer en particular que me hayan invitado, ¿no? Bien, voy a enseguida hablar de un trabajo que no es el último trabajo en el que he trabajado, pero que me pareció más adecuado para hoy, ya que es un tema un poco más clásico, ¿sí? Entonces espero que se entienda un poco mejor. Bueno, el objeto a tratar es una ecuación diferencial, o un sistema más bien, de este tipo, que es bastante vulgar, ¿no? Bastante conocido, que es un sistema de ecuaciones diferenciales en el plano. En principio, al menos en la teoría clásica, uno considera A y B funciones reales, ¿sí? Bien, entonces sobre estos sistemas, que se puede pensar que es un campo, ¿no?, de vectores, ¿sí? Existe un teorema que es realmente el único teorema de dinámica clásica completo, ¿no?, que explica cómo es el conjunto límite de una órbita de manera bastante satisfactoria, ¿no?, que es el teorema de Poincaré-Bendixson. Bueno, el teorema dice, pues básicamente, ¿no?, que siendo este un campo en plano, hay unas hipótesis que hay que suponer que hay un número finito de singularidades. De hecho, incluso la versión más redondita, ¿no?, y más perfecta del teorema se enunciaría más bien en esfera, ¿no? Siempre un campo en el plano puede extenderse, digamos, a la esfera. Uno puede pensar, por ejemplo, en la compactificación dada por la proyección estereográfica, ¿no? Entonces, cualquier, digamos, campo, por ejemplo, aquí un campo lineal que uno tenga en el plano, vía la proyección estereográfica, nos va a dar un campo también en esfera, ¿no? Claro que eventualmente puede ocurrir, ¿no?, como aquí, ¿no?, que estas dos rectas, digamos, una puede proyectarse en un círculo por ahí que pasa por el polo norte, que es el infinito, ¿sí?, digamos así. Y pues la otra recta será otro círculo que, digamos, lo voy a estirar un poquito, más bien el infinito lo voy a estirar un poquito hacia abajo. Más bien lo voy a colocar acá en infinito. No, entonces uno tiene un campo en la esfera, ¿no? Este punto que es un punto silla, uno lo tiene por aquí, ¿no? ¿Sí? Y de hecho aquí en el infinito se forman unas órbitas de este tipo, ¿no? Bueno, eso es bastante conocido. Entonces el teorema de Poincaré-Bendixson para un campo de vectores en en la esfera, pues dice que el conjunto límite, ¿no?, de una órbita cualquiera, es el conjunto de los puntos en el plano al cual la órbita se aproxima infinitamente en el tiempo, ¿no? Por ejemplo, una forma en que uno obtiene un conjunto límite es esta, una órbita que se aproxima a una órbita periódica, espiralando infinitamente, ¿sí? ¿No? Entonces ahí el conjunto mega límite, digamos, de la órbita o del punto, vamos a decir, en este caso es pues una órbita periódica. Claro, hay otro caso como el caso de la silla, ¿no? O podría ser algo acá, digamos. Aquí podría decir, ¿no?, por ejemplo, que el límite, más bien en el sentido negativo del tiempo, el alfa límite del punto P, en este caso se reduce a un único punto singular, ¿no? Es el otro tipo de límite que uno puede obtener. Y en tercer caso uno puede obtener una especie de grafo, ¿no? Como por ejemplo, una situación como esta, ¿no?, en que uno tiene aquí, vamos a poner aquí 4 sillas, y aquí uno podría tener una órbita que espirala de esta forma y se aproxima, ¿no?, a ese cuadrado, digamos, ¿no? En este caso, el omega límite de este punto P sería pues esa unión de 4 órbitas con 4 conexiones, ¿no?, entre singularidades y 4 singularidades. Bueno, y básicamente esos son los tipos de conjuntos límite que uno puede obtener en el plano, con un campo de vectores con un número finito de singularidades. Ese es el teorema de Poincaré-Bendix. Bien. Pues este teorema no tiene ninguna generalización en dimensión mayor, ¿no? Digamos, para campos en R3 o mayor dimensión no hay ninguna generalización realmente satisfactoria. Pero voy a intentar tratar este tema o generalizarlo en una dirección, que va a ser la siguiente. Voy ahora a tratar el caso de estas mismas ecuaciones, pero considerando más bien que estas A y B son funciones complejas, holomorfas. Ahora, esto es bastante natural porque, de hecho, los sistemas de ecuaciones más comunes, incluso más importantes, ¿no?, incluso si hablamos de aplicaciones, vienen de ecuaciones que están dadas por polinomios, ¿no? Voy a poner una, digamos, al azar, algo así como esto, ¿no? Por ejemplo, algo así. Entonces, este tipo de ecuaciones, si bien uno las puede considerar como una ecuación real, y por lo tanto uno tiene las órbitas reales y el teorema de Poincaré-Bendix se aplica, también por el hecho de ser polinomios, automáticamente, o digamos naturalmente, uno puede considerar que esto es más bien una ecuación compleja, ¿no?, donde el problema se trata de encontrar soluciones que sean funciones, ¿no?, x de t, y de t, funciones de una variable compleja. Y bueno, de la misma, claro, acá hay algunas diferencias que las podemos, bueno, voy a anotar acá. Vamos a ver, caso complejo. Bueno, ¿qué diferencias hay? Para empezar, ¿no?, como bien he dicho aquí, las órbitas ahora están parametrizadas más bien por un tipo complejo, ¿sí? Porque uno busca una ecuación holomorfa que cumpla estas identidades y acá la derivada es derivada en sentido complejo, o sea, la derivada holomorfa, ¿no? Entonces, estas soluciones, más bien en vez de ser órbitas, en vez de ser curvas reales, son superficies de Riemann. Voy a poner eso. Diferencias, entonces, las órbitas son superficies de Riemann. Primera cosa. sería la diferencia más importante, ¿no? Más importante, ciertamente. A ver, ¿qué otras cosas pueden ocurrir aquí? En este caso, y a ver, y dejen que redondee más el problema. Tal y como pasó en el caso real, ¿sí? Dije que era más natural enunciar el teorema de Poincaré-Bendixson más bien para la compactificación de esta ecuación, ¿no? Y la compactificación viene a ser un campo de vectores en la esfera, ¿sí? Pues en este caso también tenemos una compactificación de este sistema, ¿sí? Así que este sistema en C2 pasa a ser un sistema en una variedad compacta, que la diferencia es que ahora la compactificación del sistema se realiza, ¿no? O da origen a, ¿no? a un sistema en el plano proyectivo complejo de dimensión 2. Bien, esta es una variedad bastante conocida, pero para el que no la conoce, digamos, puede... la idea es que la principal diferencia, digamos, es que en el plano, cuando uno cierra el plano, ¿no? Cierra y forma una esfera, uno, para cerrar la superficie y compactificarla, uno solamente necesita añadir un punto. Si en el caso de hecho, el C2, siendo en realidad, al menos topológicamente, lo mismo que R4, también admite la compactificación usual. Se puede compactificar y llegaremos al FS4, pero esta compactificación realmente no es compatible con el carácter algebraico que tiene esto analítico, ¿sí? La compactificación más adecuada es el paso a otra variedad compacta que no es exactamente la esfera, ¿sí? Que se conoce como plano proyectivo complejo de dimensión 2. Bueno, pero para el que no conoce el asunto, es suficiente como hacerse una idea de que es una especie de esfera, ¿no? Compleja, sí, no es compleja. Muy bien. ¿Y cuál es la clave, digamos, del teorema de Poincaré-Bendixson? En el caso real, como les dije, ¿no? El límite de una órbita puede ser alguno de esos tipos que ya puse, un punto singular, una órbita periódica, o una especie de unión de órbitas, que aquí solamente he puesto un ejemplo, ¿no? O puede haber cosas así, ¿no? Un poco más así, también. Básicamente como un grafo. Y en particular, por ejemplo, una órbita no puede ser densa, ¿no? No hay forma de que una órbita sea densa. Y esto se debe principalmente, por ejemplo, en el caso de en que el límite es una órbita periódica, se puede ilustrar más o menos bien, es que, claro, una vez que esta órbita entró aquí y empieza a oscilar, lo que ocurre es que cerca de la órbita periódica, el flujo de los puntos está bien definido, el flujo es en ese sentido. Una vez que esta órbita llegó cerca, no tiene cómo escapar de ese flujo para volver a llegar cerca de otros puntos, o sea, y nunca va a poder en particular ser densa. Entonces la dinámica que hay está bastante bien restricta, digamos, y eso se debe principalmente a que esta órbita, ¿sí? Siendo una curva en el plano, tiene la propiedad de separar el espacio, al menos localmente lo separa, ¿sí? Cuando tú trazas una curva en el plano, esto en todo momento está separando, ¿sí? El plano en la derecha y la izquierda. Son dos, ¿no? Abiertos que no, en principio, al menos localmente, no están conectados, ¿sí? Y de hecho es por eso que el ingrediente principal en la demostración de este teorema es el teorema de la curva de Jordan, ¿sí? Que te dice que una curva cerrada simple desconecta el espacio. Bueno, pues esa realmente es la razón principal de por qué la acumulación de una órbita en el plano no puede ser muy loca, no puede ser muy... no puede ir una órbita yendo por todos lados porque ella misma se estorba a sí misma, ¿no? La órbita viene y quiere hacer lo que quiere, pero después si quiere salir, no se puede pasar a sí mismo, Si no, tendría que hacer algo así y volver a salir por el mismo lugar, pero si el sentido de las del flujo ya no lo permite, pues no podrá hacerlo. Entonces, una diferencia entonces importante aquí es que las órbitas no son separadores, al menos locales. Bueno, ¿por qué? Porque siendo superficies tienen dimensión 2, ¿sí? Pero el ambiente, que es un sistema S2, tiene dimensión 4, ¿sí? Entonces, realmente una superficie de dimensión 2 en un espacio de dimensión 4, ahí hay una, digamos, codimensión de 2, ¿no? Eso es algo así como si en R3 uno tuviera una curva, ¿no? Una curva en R3 deja una codimensión igual a 2. Entonces, eso es mucho espacio para que la curva pueda hacer cosas locas. De hecho, es por eso que, digamos, el teorema de Poincaré-Bendixson en R3 no vale está lejos de ser cierto. En particular, una órbita de un campo en R3 puede fácilmente ser densa, ¿sí? Digamos, ella va y es fácil que, como hay bastante dimensión, que se evite a sí misma y que vaya pasando cerca y vaya recorriendo todos los puntos del espacio. Bueno, algo parecido puede ocurrir acá, y es por eso que no hay un teorema tipo Poincaré-Bendixson, para nada, ¿sí? Pero voy a plantear entonces una pregunta, ¿sí? Un poquito más acotada, todavía extraída de hecho del propio teorema de Poincaré-Bendixson, ¿no? Voy a volver aquí al teorema de Poincaré-Bendixson real. Hay un corolario que uno puede extraer del teorema, que es el siguiente, y me voy a centrar en eso, ¿sí? Bueno, voy a definir qué cosa es un conjunto minimal, ¿no? A ver, un conjunto minimal va a ser un conjunto que es compacto, invariante, y mínimo relativo a esas dos propiedades. Por ejemplo, consideremos en el plano R2 la ecuación del centro, cuyas órbitas son círculos concéntricos. Bueno, aquí si uno coge, por ejemplo, este conjunto, esta especie de anillo, digamos, ¿ah? Esto de aquí es un conjunto compacto, ¿sí? Y es invariante. Es compacto y es una unión de órbitas, ¿sí? El hecho invariante es que es unión de órbitas, ¿ok? No parte de las órbitas. Entonces, sí, esto es una unión de órbitas, justamente todas las órbitas que van desde este círculo hasta el círculo de acá, ¿no? Todas estas órbitas intermedias están en conjunto. Sin embargo, este conjunto no es mínimo con esas propiedades, porque dentro de él, por ejemplo, en particular, este pequeño anillo más flaco, también es un conjunto compacto, invariante y es más pequeño, ¿sí? Así que el otro no es mínimo. De hecho, en particular, incluso, si yo cojo una única órbita periódica aquí, un único círculo, digamos, pongamos ¿no? Este de acá, del borde, solo esta órbita, ya en sí es también un conjunto compacto e invariante. Ya, pero este sí que es mínimo, ¿no? La órbita periódica sí que es mínimo porque ya no se puede, digamos, separar más. Así que, digamos que un conjunto minimal es un conjunto compacto que es indivisible dinámicamente, ¿sí? Una consecuencia directa es que en ese conjunto, ¿no? Minimal, las órbitas que estén dentro de ese conjunto, todas son densas en el conjunto, ¿sí? Es una pieza ya indivisible, dinámicamente hablando. Bueno, entonces, los ejemplos obvios de conjunto minimal, en el caso estoy aquí en el caso real, ¿sí? Pues son, por ejemplo, un punto singular. Un punto singular es un conjunto mínimo, está formado por una única órbita, no se puede dividir más, ¿no? Es compacto, obviamente, y el otro es el que acabo de decir, ¿no? Una órbita periódica. también es un conjunto minimal. Y entonces una consecuencia del teorema de Poincaré-Bendixson, inmediata de hecho, es que no existen más conjuntos minimales, ¿no? No hay otros conjuntos. No hay otro tipo de conjuntos minimales. Más que los puntos y las órbitas periódicas. Repito, esto vale para sistemas en el plano real. Bueno, entonces me voy a concentrar en este problema, ¿no? ¿Qué ocurre en el caso de los sistemas complejos? ¿Mm? En el caso complejo, pues, evidentemente, ¿sí? Los puntos singulares, por la misma razón, son conjuntos minimales. Son conjuntos minimales. Eso sigue siendo cierto. Y la pregunta sería, ¿y quién haría el papel de las órbitas periódicas? Claro, una órbita periódica finalmente es una superficie compacta. Es una órbita que es una superficie compacta. Es un círculo. ¿Sí? Entonces, es natural preguntarse si un sistema complejo tiene órbitas compactas. ¿Mm? Claro que ya hablando de dimensión 2, los modelos de superficies compactas son varios, ¿no? Pues una esfera, un toro, bueno, uno conoce un teorema de clasificación sobre superficies. Pero lo que ocurre aquí, que es a diferencia del caso real, es que no existen órbitas compactas. Bueno, aquí estoy siendo bastante laxo, ¿no? A la hora de hablar, ¿no? Pero ya, yo me estoy refiriendo ya acá al sistema de compactificado siempre, ¿eh? Es decir, la misma ecuación, bueno, también, bueno, en el transcurso de la charla voy a caer en muchas imprecisiones, pero las ecuaciones que en este caso se pueden compactificar, ¿no? A CP2 son aquellas dadas por polinomios. ¿Sí? Uno puede pensar en el plano complejo, estudiar ecuaciones analíticas en general, ¿sí? Pero acá me voy a centrar en el caso de polinomios, porque son esas las que se pueden compactificar y me dan sistemas en el proyectivo complejo. Entonces aquí estas observaciones se refieren a esos sistemas en el proyectivo complejo. Son sistemas que tienen un número finito de singularidades, ¿sí? Bueno, eso no lo he puesto acá, pero solamente lo digo. Las órbitas en este caso son superficies, ¿no? Que riman. Y no existen órbitas compactas. ¿Sí? Esto, ahora, ojo que sí existen, digamos, superficies compactas que pueden ser invariantes, ¿no? Sí puede existir, digamos, una superficie compacta, una superficie elíptica, por ejemplo, en un toro, donde quizás yo tenga un par de puntos singulares, ¿no? Entonces ahí lo que uno tendría es que sí, esto es un conjunto invariante, pero no es en sí una órbita, ¿no? El toro T, si le retiramos estos puntos singulares, ahí sí es posible que esto sea una órbita. Esta situación se puede dar, ¿no? O sea, siempre, sí puede haber superficies compactas invariantes, pero siempre tendremos alguna singularidad sobre ella, ¿sí? Entonces, en resumidas cuentas, esto no es una órbita compacta, ¿sí? Bien. Ok, entonces, tenemos los puntos singulares como conjuntos minimales, y el papel de las órbitas periódicas, que serían las órbitas compactas, en realidad no existen. Entonces la pregunta, ¿no? La pregunta aquí claramente es, bueno, ¿existe algún tipo de conjunto minimal más? Sí, en R2, como bien hemos visto, no existen más que puntos y órbitas periódicas. En este caso complejo, pues en realidad eso es un problema abierto. Problema. Existen conjuntos minimales no triviales, digamos, que no se reducen a un punto singular. Lo voy a llamar trivial a un conjunto minimal que es simplemente un punto singular, ¿no? Entonces la pregunta es si existen conjuntos minimales no triviales. Bueno, esto de hecho se suele llamar, más bien en vez de minimal no trivial, se suele llamar minimal excepcional. Bueno, les recuerdo que, por ejemplo, en el caso real, ¿no? Si uno estudia campos en R3, ahí uno puede encontrar conjuntos minimales más allá de un punto de una órbita periódica, ¿no? Por ejemplo, uno puede pensar en un toro con un flujo irracional, ¿sí? Eso se puede realizar como un conjunto invariante de algún campo de vectores, ¿no? En R3, por ejemplo, o en R4, incluso más fácil. ¿Sí? Así que sí, se pueden, en general uno podría esperar que existan algún otro tipo de conjuntos minimales, pero lo cierto es que ese es un problema abierto. Difícil, ¿no? Diría que por ahí un poco más, quizás un poco más de gente estaría inclinada a pensar que no existen, pero en realidad tampoco no hay razones así tan sólidas como para creer eso, así que realmente no se sabe. Bien. Entonces, ¿qué vamos a hacer ahora? ¿O de qué se trata el resultado que voy a contar? Voy a hacer, digamos, un paralelo o algún teorema similar a este, pero en un sentido local. ¿Y qué quiero decir con eso? La dinámica, voy a volver otra vez a R2, ¿eh? En R2. En R2, ¿sí? Por ejemplo, aquí tengo una masilla, ¿sí? Una cosa así. Ahí está. Y aquí podría tener algún otro punto singular, así. ¿No? Bueno. La dinámica, o sea, el hecho de que yo obtenga un conjunto límite complicado, ¿sí? Siempre se da, o sea, ¿sí? Una órbita puede ser, digamos, muy loca, moverse por todos lados de manera loca, solo por motivos globales. Solo porque, por ejemplo, ¿no? Cuando una órbita tiende aquí, en realidad consigue aproximarse a todos estos puntos, ¿no? Recurrir en todos ellos en el tiempo, porque la órbita lo que está haciendo es realmente ir, volver, necesita, digamos, espacio, ir y volver para conseguir hacer eso, aproximarse a un montón de puntos aquí al mismo tiempo. ¿Sí? Y la pregunta es si es, y de hecho este tipo ¿no? de aproximación a muchos puntos no se puede dar si no tienes espacio. ¿Qué quiere decir? Por ejemplo, voy a dibujar para ilustrar esto en R2, el caso de singularidades, y me voy a referir a puntos singulares justamente porque son los únicos puntos donde yo puedo tener alguna dinámica, ¿no? En los puntos regulares tenemos el teorema de flujo tubular, así que la dinámica digamos que es trivial, ¿sí? Y cualquier recurrencia aquí se debe a motivos globales, ¿no? Porque las órbitas van lejos y vuelven, ¿sí? Pero en los puntos singulares yo podría tener, en principio, alguna dinámica rica local. Aunque en R2 realmente prácticamente eso no ocurre. Por ejemplo, a ver, en el caso de una silla en R2, así, claro, este punto se acumula el punto singular, pues y nada más. La pregunta es si algún punto podría acumularse a más que el punto singular, así. Algún punto aquí cerca podría generar una acumulación, un conjunto límite más grande, pues voy a poner este ejemplo, ¿no? El ejemplo que ya puse hace un rato. 4 puntos singulares y una órbita que hace esto. Digamos, digamos que este punto P. Entonces, el omega límite de P, ¿sí? El omega límite de P, el límite de P, se compone en realidad aquí, bueno, de hecho de todo este cuadrado, ¿no? Pero si yo, al decir que me voy a preocupar por un problema local, quiero decir que me voy a fijar en una singularidad, por ejemplo esta, y yo quiero fijarme qué está pasando cerca de ella. Entonces cerca de ella lo que podemos ver es que el punto P origina un conjunto límite que se compone del punto singular y de dos órbitas ahí. ¿Sí? Ya, entonces digamos en principio ahí tengo que se genera aquí cerca del punto singular una acumulación más grande, pero ojo que esto tiene un defecto, una salvedad, que es que la razón por la cual ese punto P consigue aproximarse a los puntos verdes es justamente porque el punto P sale de cerca de acá y tiene la posibilidad de irse lejos y poder retornar, ¿no? O sea, finalmente la razón del por qué el punto P se puede acumular en este conjunto grande es una razón global, nuevamente, y no local. O más concretamente, ¿qué quiere decir con esto? Es que si yo reduzco, me reduzco una vecindad aquí, digamos aquí, este punto singular, entonces lo que va a pasar aquí es que esta órbita se rompe, ¿no? Esta órbita de P se rompe y lo único que me queda se me separan un montón de órbitas, en infinitas órbitas. Pero entonces ya ninguna de estas órbitas en realidad se está acumulando al conjunto verde. Ninguna. Ninguna por sí sola. Entonces en realidad aquí, en este sentido quiero referirme a conjuntos, digamos, límite, pero locales. ¿Sí? Son conjuntos límite que se generen cerca de un punto singular, pero que se generen cerca del conjunto singular. Que no necesite la órbita irse lejos y volver. Eso sería como hacer trampa. ¿Sí? Entonces, claro que esa situación en R2 no se da, y eso es lo que estoy mostrando con esto. En los otros casos lineales, uno puede, por ejemplo, recordar sistemas como este, ¿no? Donde, bueno, el conjunto límite de las órbitas es solo un punto, ¿no? Realmente no se puede conseguir acumulaciones más grandes en un punto singular, ¿sí? De forma local, ¿no? Siempre se consiguen solamente si la órbita se le permite ir y dar un paseo lejano, digamos, ¿no? Entonces, voy a resumir, digamos, esto diciendo que un punto singular en R2, digamos, un sistema R2, no tiene bueno, a ver, acá voy a saltar un poquito en el argumento, pero es que si yo tuviera alguna acumulación grande, ¿no? Que no la tengo en R2, ¿no? No la tengo en R2. Eso me permitiría encontrar una especie de conjunto minimal local, digamos, asociado al punto singular. Y esta conclusión se basa en el lema solo. ¿Sí? No lo voy a discutir ahora, pero es un digamos, yo tengo, de hecho, esa sería la prueba de que existen, si yo tengo un conjunto K compacto, invariante, no digo minimal, compacto invariante, pues entonces, dentro de él, yo puedo encontrar un compacto invariante y minimal. Y la prueba de eso se basa, pues, en el teorema de Sol, en el lema de Sol, ¿sí? Entonces, digamos que finalmente esta pregunta se podría, no estoy haciendo las definiciones adecuadamente, pero como me interesa el caso complejo, en el caso complejo lo dejaré un poco más claro, ¿ya? Aquí simplemente acabaré diciendo que un punto singular en R2 no tiene minimales locales. Bueno. Esa es una forma un poco más codificada realmente de decir, más sofisticada, de decir que lo que dije hace un rato, ¿no? Que una órbita no se puede acumular en un conjunto más grande que el propio punto singular, a menos que la órbita se le permita hacer paseos largos, ¿no? Pero de manera local no puede. Es simplemente eso. Bien. Ahora, este problema que realmente es trivial aquí, trivialmente uno nota que esto realmente es así, esto es una verdad. En el caso complejo ya no es nada obvio, ¿no? Y de hecho ahí pueden pasar cosas muy interesantes incluso a nivel local. Bueno, voy a hacerlo así, voy a hacerlo aquí. Ya. Voy a poner aquí, pero en C2 sí ocurre. Sí ocurre. ¿Sí? Ya. Entonces, solamente para mostrarlo, voy a dar algunos ejemplos. bien sencillos, ¿sí? De cómo esto ocurre. De hecho, me voy a centrar en un ejemplo. Va a ser el más importante. Va a ser el siguiente. Entonces voy a considerar este ejemplo. Ejemplo. Este tipo de singularidad se llama singularidad nodal o simplemente se dice que es un nodo. Y se trata del sistema, pongamos ahí, lambda 1x, lambda 2y. Complejo, sistema complejo, ¿no? Bueno, este sistema se resuelve no explícitamente, muy fácilmente, una solución, digamos, que pasa por el punto inicial x0, y0, ¿sí? Finalmente la órbita se parametriza de esta forma, ¿no? Es x0 exponencial lambda 1 t, y0 exponencial lambda 2 t. Digamos que una órbita o una hoja, ¿no? En este caso, tiene una parametrización de este tipo. Como es un x0 y 0 el punto de inicio, un punto por ahí, ¿no? Fuera de los ejes. ¿No? Bien. Vamos a suponer, además aquí, que este cociente es un número irracional positivo. Y ese ejemplo va a ser muy importante. A ver. Bueno, entonces una hoja aquí genérica es parametrizada de esta forma. ¿Ok? Aquí, de hecho, incluso sería más fácil incluso de considerar este sistema. Voy a alterar un poquito que va a ser más sencillo. Puedo suponer que este es un 1, ¿no? Por un cambio lineal, de hecho. Y colocar más bien aquí lambda 2 sobre lambda 1, ya para simplificar esto. Así que, de hecho, mejor voy a poner aquí lambda, ¿no? Y directamente, o al revés, ¿no? Pero bueno, así. Real positivo, pero no racional. Entonces, me quedaría así, ya. Es lo mismo, pero ahí está un poquito más tratado. Bueno, es fácil ver que, ¿no? Un punto cualquiera de L, ¿no? Si x, y pertenece a L, se ve fácilmente, ¿no? X tiene esta forma, Y tiene esta forma, se ve, digamos que al ojo, que ahí se cumple esta identidad. Se cumple que Y, ¿sí? Dividido por, en módulo, X a la lambda. Ojo que lambda es un real positivo, así que puedo hacer esto sin mayor problema. Esto es una constante. Se ve claramente, ¿no? El lambda se va a cancelar esa parte, va a quedar una constante que de hecho es y0 sobre x0 en módulo a lambda. Bueno, esto es una superficie, ¿sí? Voy a llamarle, de hecho, S a esa superficie, que es una superficie de esta forma. Constante, x lambda. ¿No? Eso es. S2, ¿no? Esto es una superficie tridimensional, ¿sí? Tridimensional, ¿sí? Y es singular en el origen. En el origen. Bueno, es fácil ver que esto realmente dado por una única ecuación real, porque esto es módulo, esto es algo que espera que sea de dimensión 3, ¿sí? Y un ejercicio aquí, ¿no? Lo voy a dejar como ejercicio porque es realmente bastante fácil. Bueno, no bastante fácil, pero es bien accesible a cualquier alumno. Es que, de hecho, esta hoja no solo está contenida, que obviamente está contenida en este conjunto, sino que es densa en ese conjunto. La hoja que está contenida en ese, de hecho, es densa. De hecho, todas las hojas en ese son densas, ¿no? Todas las hojas en ese son densas en ese. Así que este sería mi ejemplo. Y ahora voy a decir, además, voy a intentar hacer aquí un dibujo de lo que estaría significando esto. Es una cosa así, ¿no? Entonces tengo C2, ese conjunto Y igual constante X lambda, es una cosa de dimensión 3, que bueno, lo voy a dibujar así porque es una cosa singular. En realidad, acá lo dibujo como una trompetita, ¿ya? Pero un dibujo más cercano en realidad sería algo así, imagínense. ¿Ok? Y lo que ocurre aquí es que la hoja L, ¿no? La hoja L es esa, en ese conjunto de dimensión 3. Pero otra propiedad más ocurre aquí, que también es, puede ser otro ejercicio, eso es fácil de verlo, no es difícil de ver. Es que si yo intersecto este conjunto S, lo intersecto con una esfera, esta intersección, va a tener dimensión 2, claro, ¿no? Es una, o sea, un corte, intersección es difeomorfo un toro. Y no solo eso, sino que digamos, el retrato de fase que yo tengo ahí, la foliación que yo tengo ahí, porque la hoja misma L, que está por aquí, ella también está cortando esta esfera, así que, y bueno, y la corta en curvas reales. Esas curvas reales son órbitas aquí que me conforman un flujo lineal irracional en el toro. Toro con flujo irracional. Y de hecho, claro, ya podemos sospechar que el número de rotación, ¿no? es justamente ese exponente lambda irracional que aparece ahí. ¿Sí? Pero bueno, pero lo que ocurre aquí, y esto es parecido a lo que ocurre con las curvas, ¿no? Las curvas analíticas, ¿no? Los puntos singulares de curvas analíticas. De hecho, este conjunto tiene una estructura de cono, una estructura cónica. Esta propiedad vale para cualquier esfera, ¿sí? Y las hojas L son transversales a todas las esferas, ¿sí? Así que, de hecho, esa propiedad de que la hoja L es densa en esta superficie, en esta trompeta, de hecho, lo que ocurre es que en cada nivel, ¿no? Porque yo tengo un toro con un flujo irracional, o sea, la hoja está siendo densa en cada nivel. No, digamos, si yo parto con un puntito aquí en la hoja L, ¿sí? Yo sé que la hoja L va a ser denso en todo, pero yo no necesito irme lejos para realizar esta densidad, porque esto, de hecho, consigo moverme dentro de la hoja, aquí cerquita, de hecho, dentro del conjunto verde incluso, y conseguir llegar pues densamente a todos los puntos aquí y a todos. O sea, aquí efectivamente estamos hablando de una hoja que produce un conjunto límite grande, pero lo produce de manera local, no necesita irse lejos. Y por más que tú reduzcas la vecindad, la hoja L va a seguir haciendo su trabajo, va a seguir consiguiendo ser densa, ¿sí? En ese conjunto S. Entonces, digamos que aquí la conclusión es que este conjunto S, para definir esto correctamente, yo estoy siendo muy laxo en todo el asunto, ¿no? Pero este conjunto S se entiende en el sentido de los gérmenes, ¿sí? Digamos que es un germen de conjunto minimal local, ¿no? Entonces, esto sería un ejemplo de que tiene este nombre: separador nodal. Y es un ejemplo de conjunto minimal local, en ese sentido que más o menos he explicado. Cosa que no existe en R2, ¿no? Para singularidades en R2. Aquí existe. Bueno. Entonces, ¿de qué trata, ya que existen estos conjuntos? Ahora la pregunta es, ¿existen otros? Y la respuesta básicamente va a decir que, bueno, solo existe este y existe uno más, que de hecho va a ser más fácil de escribir ahora mismo. Digamos, esta manera de introducir el teorema por medio de minimales locales, como les dije, es una forma un poco más sofisticada de presentar el resultado, pero para que quede más clarito, voy a presentar el resultado de una forma que va a ser equivalente, pero quizás va a ser más comprensible, ¿sí? Entonces paso a enunciar cuál es este teorema. Ojo que este separador nodal, de hecho, para discutir el nombre separador es porque justamente es un separador. Tiene dimensión 3. Teniendo dimensión 3, realmente separa el ambiente aquí en dos regiones invariantes. ¿Sí? Entonces, para enunciar el resultado, voy a recordar aquí un teorema. ¿No? Teorema de Camacho y Isaac. Todo singularidad. Acá me refiero a una singularidad de un sistema complejo en dimensión 2, ¿no? Toda singularidad voy a poner aquí en dimensión 2. Pero me estoy refiriendo a sistemas holomorfos analíticos en dimensión 2, ¿no? Dimensión 2 compleja. 2 compleja. Admite una separatriz. Ya, es un teorema muy importante, muy famoso. Explico qué cosa es una separatriz. Por ejemplo, un caso especial de sistemas son aquellos dados por integral primera, ¿no? Como en R2 también, ¿no? O sea, si yo quiero un sistema, un retrato de fase singular, una manera de obtenerlos es, por ejemplo, si yo tomo una función, por ejemplo, la función f igual a xy. Entonces, aquí, los niveles xy igual constante, de hecho son así, ¿no? Me producen un retrato de fase. ¿Y qué es el retrato de fase de un campo? El campo ahí, hamiltoniano, no social. Ya. En fin, cuando este es un tipo especial, digamos, de punto singular, ¿no? Pero este tipo especial de conjunto, de punto singular, digamos, los que son dados por los niveles de una función, ¿sí? Aquí es evidente el teorema, ¿sí? Es evidente el teorema porque, digamos, voy a poner que la función en el origen, ¿sí? Vale 0, ¿ya? Entonces, si en el origen la función vale 0, de hecho, yo tengo un montón de otros puntos, digamos, estoy en dimensión 2, ¿no? Donde la función vale 0, ¿sí? Este sería el nivel 0, digamos. En este caso de la función que he dibujado acá, el nivel 0 se compone de estas dos rectas, ¿no? Pero tú podrías tener otros ejemplos, digamos, esto es x cuadrado menos y cubo, pues ahí el nivel 0 sería la curva x cuadrado menos y cubo igual 0, que es una curva singular, ¿no? Digo, menos en R2 no puedo dibujarla así, ¿sí? Pero todos los niveles, los otros niveles, f igual constante, pues son niveles que están por aquí y así, ¿no? Bueno, es un retrato de fase donde yo tengo un punto singular, pero donde yo tengo evidentemente una separatriz. ¿Qué cosa es una separatriz entonces? Una separatriz es justamente una curva que es invariante y que pasa por el punto singular. Es una especie de digamos, pseudo solución en el punto singular, ¿sí? Recuerden que el teorema del flujo tubular te dice que en un punto que no es singular, yo siempre tengo una órbita de campo. Ahí está. Esa sería como la separatriz, digamos, en ese caso trivial, ¿no? Pero en un punto que es singular, no necesariamente existe algo así, ¿no? Por ejemplo, en el caso real, si yo considero la ecuación del centro, pues aquí, en este retrato de fase, no hay ninguna curva invariante que esté pasando por acá. No existe, ¿sí? Pero, en el caso de ecuaciones complejas, siempre existe, ¿no? Siempre existe. Ahora, de hecho, esta ecuación del centro, ¿no? Que está dada por este sistema, ¿no? Menos y punto igual x. De hecho, también es un sistema complejo, ¿no? Y cuando uno considera esto como un sistema complejo, la separatriz que existe según el teorema es una curva que en realidad está en la parte compleja, ¿no? Digamos que está así, pasando así. Entonces, separatriz es un conjunto, invariante de la forma dado por que es una curva, ¿no? Dado por la ecuación, por una ecuación analítica, ¿sí, no? Eso es. Que contiene origen, ¿no? De la forma que contiene al origen. ¿Qué contiene al origen? bueno, al punto singular, contiene al punto singular. Eso es. Bueno, de hecho, donde esta f es una función analítica, de hecho, irreducible. Siempre se pide que sea irreducible, ¿sí? Entonces es una rama de curva. Bueno, esto siempre existe, ¿sí? Y listo, entonces, este tipo de conjunto, por ejemplo, ¿no? en el caso que puse aquí de la silla, ahí tengo un montón de órbitas que son acá, pero una silla existen dos separatrices. Una es esta, el eje X, y la otra separatriz es el eje Y. Recuerden que estando esto en dimensión 2 compleja, esta órbita, ¿sí? En realidad esta órbita no contiene el punto singular. El punto singular es una órbita por sí mismo. Este eje me refiero, digamos, al plano C perforado, ¿no? Quitándole este puntito que es el punto singular. Pero esto es una órbita, ¿sí? Y no se puede dividir más, ¿no? Entonces ahí, también aquí ya queda en evidencia que de hecho mi definición de conjunto minimal, ojo, permite, este conjunto minimal de hecho contiene dos órbitas y contiene el punto singular, pero el punto singular, digamos, estrictamente hablando, ya sería un conjunto más minimal, digamos, ¿no? Entonces, para este estudio local, mi definición de conjunto minimal, de hecho, es conjunto minimal a menos que sea el punto singular, ¿sí? O sea, el punto singular es demasiado trivial. Yo me estoy interesante en conjuntos minimales, pero que no sean un punto singular, ¿sí? Bueno. Entonces, este es el otro tipo de objeto que puede ser un conjunto minimal, en este caso. Entonces, el teorema, ese es un teorema con Camacho, ¿no? Pues dice que los únicos minimales para singularidades en dimensión 2 hay que definir bien lo que es minimal, de acuerdo a lo que explicaba, ¿no? De singularidades en dimensión 2, ¿no? Compleja, son las separatrices y los separadores nodales. Ojo que el separador nodal que definí fue nada más un ejemplo, ¿ya? Un ejemplo. Ellos se pueden presentar en otras formas, así como pasa con las separatrices. Las separatrices son curvas, esencialmente. En el caso de la silla, ¿sí? Te dije que el eje X es una separatriz. O sea, esto es una separatriz. Esta es una curva presentada, de hecho, de la forma más simple posible, ¿no? Es una curva regular, ¿sí? Pero las curvas sabemos que pueden ser presentadas de forma más compleja. Una curva puede ser una cosa así, por ejemplo. Bueno, todos esos casos pueden entrar aquí. Pero quien conoce un poco más de esta teoría de curvas o los teoremas de resolución de singularidades, sabe que esencialmente, a menos de manera intrínseca, esta curva igual es, ¿no? Ella es, digamos, difiomorfa a un disco también, ¿no? A un disquito. Como esta, ¿no? Digamos, acá localmente es difiomorfa un disco. Solo que esta está anudada en el ambiente, ¿sí? Está anudada. Es este mismo disquito, pero anudado ahí localmente. Entonces lo mismo puede pasar con un separador nodal. Yo les presenté el separador nodal, digamos, más simple, digamos, el más recto posible, pero él mismo podría aparecer de forma anudada en distintas... de forma muy complicada, de hecho, ¿sí? Pues bien, a ver si tengo 5 minutos. Quizás la otra forma, ya que no está del todo bien definido, no definido bien qué cosa es un minimal. En realidad acá minimal, los únicos minimales tendría que decir aquí de que no es lo mismo, los minimales locales, ¿no? A eso me refiero. Pero bueno, yo puedo parafrasear este teorema de una forma quizás más sencilla de entender, es que si una hoja L se acumula en el punto singular, es tal que el punto singular, digamos que es el origen, ¿ya? Este es el punto singular, ¿eh? Tal que el punto singular está en la clausura de la hoja, entonces, esta clausura también contiene, pues, o bien una separatriz, o un separador nodal. O un separador nodal. ¿Esto qué quiere decir? Que, digamos, en un punto singular pueden haber separatrices, ¿no? Y puede haber separadores nodales por aquí, no sé, una singularidad muy complicada, ¿no? Si yo tengo una hoja, ¿sí?, que se acumula en el punto singular, si ella consigue recurrir en el punto singular, entonces no puede recurrir solo en el conjunto singular. Si recurre en el conjunto singular, es porque también se acumula o bien en una separatriz, o bien en un separador nodal, ¿no? Eso es lo que dice el teorema. Entonces, para que una hoja consiga acumularse aquí de manera local, necesariamente tiene que acumularse en algo más grande, o bien una separatriz, o incluso un separador nodal que tiene dimensión 3. Entonces, es otra forma de presentar el teorema. Bueno, no tengo realmente más tiempo como para dar una idea de cómo viene la prueba. Solo para terminar, me gustaría mostrar en todo caso una aplicación, ¿no?, de este resultado a un teorema global, ¿sí? De hecho, la pregunta inicial era si en un sistema, en el proyectivo complejo, puede ser una cosa así, ¿no? Tener muchos puntos singulares, así, qué sé yo. La pregunta era si existe algún conjunto minimal excepcional, ¿no? O sea, que no sea un punto singular. Si existe algún conjunto minimal ahí, no sabemos si existe, la verdad, pero una consecuencia de este teorema local es este resultado, junto con Arturo Fernández, Rogerio Moll, es que si existe un minimal, ¿no?, todo minimal excepcional, o sea, un conjunto minimal excepcional es, voy a poner aquí, atrae a todas las órbitas. ¿Esto qué quiere decir en este sentido? En el sentido de que si existe este minimal excepcional, entonces cualquier hoja que tú cojas, cualquier hoja, en su acumulación, ¿sí?, va a contener el conjunto minimal, ¿no? O sea, podría ponerlo así. Para toda hoja L, vale que el conjunto minimal está incluido en la clausura de L, ¿no? Un minimal excepcional, entonces pondremos aquí, excepcional M atrae a todas las hojas. O sea, esto. Que es una cosa no trivial, ¿sí? Es un poquito sutil. A ver, solo para decir entonces en 2 minutos cuál es la idea de la prueba. La idea de la prueba y cómo se usa el teorema local para hacer la prueba de esto. Pues, bueno, a ver, cojamos una hoja L, digamos esta, y probemos que la clausura contiene el minimal. Supongamos, de hecho, que no es así. A este conjunto, esta hoja L la voy a pintar de azul. Bueno, pero la clausura de la hoja, yo sé que es un conjunto invariante. Digamos, la clausura de la hoja es un conjunto invariante que pasará, pues así, no sé. Supongamos entonces que esto no es cierto, ¿no? Si no lo contiene, entonces son disjuntos. O son disjuntos, no puede intersectarlo parcialmente porque este es minimal, esto no se puede separar. Son disjuntos. Si son disjuntos, ambos son compactos disjuntos, entonces yo puedo encontrar, digamos, sus puntos de mínima distancia, digamos así, ¿ya? Entonces yo puedo encontrar ahí un puntito, digamos aquí, y un puntito aquí, tal que estos están a distancia mínima, ¿ya? Digamos, más o menos esa es la idea, ¿ya? Más o menos esa es la idea. Entonces yo diría, ok, el minimal, como no tiene puntos singulares, De hecho, esa distancia mínima se está realizando en un punto aquí, y en el azul un punto aquí. Voy a hacer el dibujo acá. Tengo así, un punto aquí, y en el otro tengo un trozo de hoja y un punto aquí, y aquí se realiza la distancia mínima. Pero esto no va a ser posible porque estos son, digamos, estos son como gráficos de funciones, holomorfos. Entonces yo estaría diciendo que esta función holomorfa tiene un mínimo, o su módulo, digamos, tiene un mínimo aquí. Y por el principio de módulo máximo es imposible. Salvo que, claro, este mínimo aquí no, porque esta clausura yo no sé qué puntos tiene. Aquí estoy suponiendo que este punto de la clausura es un punto, digamos, regular, pero podría ser que no lo sea, y que ese mínimo, más bien, sea un punto singular. ¿Qué tal si ese mínimo es un punto singular? Y aquí no sé cómo será L, pues será una cosa así, digamos. Quizás es así, un separador, una cosa así. ¿No? Entonces ahí aplicamos el teorema, ¿no? Bueno, si esto es un conjunto invariante que contiene este punto singular, entonces si este conjunto se acumula en el punto singular, se acumula en algo más, o en una separatriz, o en un separador nodal. Si fuera una separatriz, quiere decir que yo tendría una curvita aquí, así, ¿no? Como x cuadrado menos y cubo igual a 0. Y ahí, digamos, con los dibujos ingenuos que uno hace así en R2, uno podría decir, bueno, entonces sí podría ser que esta puntita esté más cerca que el resto, ¿no? Pero en realidad eso no ocurre, ¿no? De hecho, cuando uno dibuja la cúspide, como les dije así, un dibujo más correcto de la cúspide compleja sería más bien hacer algo así, ¿ya? Porque en realidad aquí este dibujito da la impresión de que si tienes la cúspide y se te cae al suelo, podría caer de punta, ¿no? Esa es la impresión que da. Pero eso no puede ocurrir, ¿ya? Porque la cúspide en realidad es así. Si se te cae esto al suelo, el punto singular nunca cae de punta. Está lejos de todos lados. Entonces, en realidad, esto es una cosa así. Y por esa razón, como está bien dentro, digamos, este no puede ser el punto más cercano. No puede ser. Así que se descarta este caso. Y en el otro caso, si no es una separatriz, entonces puede ser un separador nodal. Ahí está, separador nodal. Pero con el separador nodal pasa lo mismo, ¿no? De hecho, el dibujo más adecuado es una cosa también así. O sea, y eso es algo que ya menos, no trivial, no hay que demostrarlo, es que el separador nodal, que es una variedad de dimensión 3, y de hecho no es una variedad analítica real ni nada, es una realmente trascendente aquí, pero aún así ella tiene la propiedad del módulo máximo, ¿sí? Este puntito, mejor dicho, si se te cae el separador nodal, no se va a caer el punto. ¿Sí? Y por lo tanto tampoco puede hacer este caso, y así que el único caso que se da es el que grafica al inicio, y esa es la prueba. Bueno, para el que esté interesado en el tema, realmente los ingredientes, ¿no? para demostrar estas cosas, bueno, principalmente es los teoremas de resolución de singularidades, ¿no? de campos, ¿no? De curvas incluso. Y algunas cuestiones ahí topológicas, ¿no? No tan complicadas, pero principalmente es la noción esta de cómo resolver singularidades. Bueno, entonces, gracias por su atención.
Okay, so thank you very much, Professor Rudy Rosas, for your talk. And first of all, let's thanks to him. Thank you. Is there any question from the public? Remember that you can also write it down in the chat, in the Zoom chat, all your questions, you can write it down there. Okay, if there's no questions, so let's thanks again, Professor Rudy Rosas.
Gracias a todos por su atención. Y
thank you very much. Muchas gracias. And so we're gonna take a break, and we're gonna return at 4 p.m. Peruvian time zone to the next
seminar. Thank you. Sí, en 5 minutos. Buenas tardes. Good afternoon. You are going to start in about 5 minutes. Please wait. Thanks for your patience.
Hola, Alfredo.
Prendió mi audio, pero sí, ahí estoy.
Ahí estoy.
¿Y qué tal todo?
Bien. Hoy día mi hija está rindiendo los exámenes para entrar a la universidad.
Eso es justo lo que te iba a preguntar.
Bueno, fue hoy día en la mañana y después le toca mañana, en la mañana y en la tarde.
¿Y qué va a estudiar?
Creo que quiere psicología.
A mí me agarraron con arqueología, antropología y la otra lingüística. ¿Sí?
Pero tú ya terminaste, po.
Sí, yo terminé ya y espero que un par de años ya terminar y dedicarme a leer. ¿Pero cuántos años tiene ya? 16, 17 años.
¿Quién no? 18.
Tamara.
Tamara. 18.
18.
Y el otro tiene 15.
Don Andrés.
Don Andrés está más alto que yo.
Y tú eres relativamente alto. Chato no eres.
Un 84, una cosa así también. Mide él.
¿Y cómo andan ahí con la pandemia?
Bien, yo creo que mejor que ustedes, ¿no?
Acá no se ha terminado de ir, oye. O sea, acá seguimos teniendo 20 muertos diarios todavía.
No,
O
bueno,
sea, no
aquí
ha habido días sin muertos desde este año, por ejemplo.
no, nosotros también.
Ustedes más bien salió tremendo anuncio que, por primera vez, que no.
No, pero eso fue un día que estaba cerrado el registro para...
Cerraron la morgue, ¿no?
No estaban de vacaciones.
Bueno, esperemos que por ser verano sea más tranquilo, ¿no?
Sí, yo también espero. Pero ustedes ya empezaron a hacer clases presenciales, ¿no?
No, pero ya nos han amenazado que el próximo semestre lo pensemos seriamente para...
Yo he hecho clases híbridas este semestre.
No, yo escribía mi clase y no sé cuánto, me la he pasado escribiendo, desde hace 1 año y medio escribo, y escribo, y escribo, y escribo, y escribo. Oye, supongo que tienes el correo de Juan en Rochester. Si me lo puedes mandar cuando puedas, si te acuerdas.
Ya.
Okay, very good. So we are continuing with the next seminar, and we will have the presentation of Professor Jan Kiwi. He is a researcher on Pontificia Universidad Católica de Chile. His main research interest is dynamical systems. So it's a pleasure to have you here, Professor Jan Kiwi, and it's your time to talk. Thank you.
Well, many thanks for the invitation. It is always nice to be in Lima. Also, well, I suppose that at the end of the talk, you can explain me what is the meaning of 38 movements. I was tempted once to retitle my talk as the tale of 2 movements. So I'm just going to talk about 2 movements, 2 movimientos, which is, of course, much less ambitious than 38. So, okay. So let me start. So, well, Araceli and Mathieu talked a lot about the object, the main object that I'm going to talk about, but anyhow, let me remind you a little bit what we're talking about. So we're talking about, so we are going to be working in a space of cubic polynomials that are critically marked. A cubic polynomial, a typical cubic polynomial has 2 critical points. And if you choose a pair, a polynomial and a critical point, that is a critically marked cubic polynomial. And you can talk about equivalence classes of these polynomials, that is that the 2 polynomials are going to have the same dynamics, 2 critically marked cubic polynomials are going to have the same dynamical behavior if you have an affine transformation that so a pair F omega and a pair G omega prime are in a certain sense the same dynamical system if there exists an affine transformation such that this happens and A of omega prime is equal to omega. Okay? So, so the space of all these things are 2 complex dimensional parameter space or space of polynomials, which we can see, we are going to see that it is just the complex plane that is C2 mod out by an involution. So you can think of this space just if you want just as a C2 or it is just a surface, something cut out by one equation in C3. And if you look at there's this special slice that Araceli and Mathieu were talking about, which are all the cubic polynomials which have the critical point omega, periodic of period exactly k. Okay? And that is the periodic curve of period k. And Milner in the 90s started a systematic study of these curves. He proved that they were smooth and asked whether they were connected or irreducible, these two words, once you know that the curve is smooth, mean the same thing. But I still like them, both of them, to appear in my talk, because one is more in the algebraic side and the other is more in the topological side. I will be working more in the topological side, but to put into context the question, it is good to understand that there's also an algebraic side to the question. Irreducible comes from the fact that proving that this is connected is equivalent to proving that certain polynomial is irreducible, okay? In certain ring. Okay, so let me put the question into context, and I also would like to put it into context the techniques that we're going to use to tackle this question. So this family of curves in the space of cubic polynomials with a marked critical point are part of a larger family of curves, which I denote SLK, which are formed by all the polynomials for which the marked critical point takes L iterates to map to a period K point. So here's the marked critical point. You iterate L times, and it becomes a period K cycle. Okay. And if you look at all the cubic critically marked polynomials modulo affine conjugacy that have the marked critical point being eventually periodic of period K, and that in L iterates falls into a periodic period K orbit, that is denoted exactly by this symbol. And it turns out that this guy is also smooth. So the question about the reducibility and connectedness is equivalent. And recently, Xavier Bouffe, Epstein, and Sarah Koch showed that for all L greater or equal than 0, the eventually fixed so you wait L iterates, and then you land at a fixed point. That curve is irreducible. And they actually prove this more in the irreducible side of the techniques. I mean, more with techniques that are more in the algebraic side. And my master student that said that he was on YouTube watching this is now writing his master's thesis, adapting the techniques that we used to the case to recover Epstein's Bouffe-Epstein-Koch result using these more geometric techniques that are more in the topological side to prove that this is connected, okay? So that is one, so there's this, there's a whole, here's a open census. This is organized by grad students. So now the homework for you is to show that these guys are irreducible, okay? So that is open. This in Aracelis talk, somebody asked why one should study these things, and somehow Jack started answering, and I was proctoring an exam at the same time, and a student asked a question, so I couldn't listen to Jack's answer. Okay, but one of the I sort of heard this keyword about that all postgridly finite hyperbolic polynomials were there. Okay, I think that I heard that. So, but these curves, all the SLK, belong to what now are called special curves, which are there's this beautiful theorem by these people that they show that if you have an algebraic curve of cubic polynomials containing infinitely many postgridly finite polynomials, then it has to be a component of one of these three types: the curves SLK, or you have a curve that is cut out by a critical orbit relation of the type. There's another way of having relations, which is you have one critical point and you have the other. I'm being loose here because I didn't mark the two critical points. Okay, but okay, so this is this type where omega comes into omega prime. Okay, or you are in the symmetry locus. That means that you have an affine, non-trivial affine transformation that commutes with your maps, okay? Where A is not the identity. So in a certain sense, these curves belong to are the case 0K of the special curves. Let me put another context in which similar questions are addressed. Is the context of quadratic rational maps. Quadratic rational maps is also the moduli space, or has a dimension 2. There are two critical points. So there's some analogy between what happens. So what happens in cubics should be an easier version of what happens in quadratic rational maps. So the same question about the reducibility of periodic curves is quite open. There was a hope of trying to tackle this via something that Epstein introduced that are deformation spaces, but it was shown that the period for deformation spaces are disconnected, so no way of tackling in that direction. There's a beautiful work by Rohini Ramadas and Silversmith, which they completely parameterize the period 5 curve, which is an elliptic curve, and they compute the J invariant. They tell you everything you want to know about that curve. And the good thing about the proof by Xavier, Adam, and Sarah about eventually fixed curves in the cubic case is that the same argument pushes to the quadratic rational maps. Okay, so they work with more algebraic methods, and their algebraic methods also can be applied to prove that eventually fixed curves, so these corresponding S0, SL1 in the space of quadratic rational maps, are irreducible, and our technique with Mathieu completely, I mean, I have no idea how you can generalize them for quadratic rational maps. Another context which is going to be particularly relevant for us is the context of what is called anatomic curves. The anatomic curves were initially, I mean, the first result was proven by Bush in his thesis, And well, and then generalized by Lau and Schleicher. The D here is this is equal to D, where you take in C2, you take the horizontal, I mean the x-axis is going to be your parameter C, and your y-axis is going to be your dynamical plane, and you look at all the points where this is C and all the periodic points, of period N, essentially, and being also like not completely precise here, but okay. So so you have this sort of graph, and both showed that these the anatomic curves are also connected or irreducible, and the technique that he used is sort of related to what Wolf, Epstein, and Koch did, and then the proof given by Lau-Schleicher is more geometric or topological, and is in certain sense closely related to what we are going to do now. So this was to sort of give you a flavor that there are many contexts in which questions about irreducibility arise. The questions are motivated by this general issue that maybe I should have said before, that for example, suppose that your curve SK has 2 components. Then the natural question is to say, well, what is, so there are dynamical systems here that have a marked critical point of period K, and there are dynamical systems in the other component which have the marked critical point of period K. So then you should ask, what distinguishes between these two components? What makes some polynomials be together here and some polynomials be together here? And it is hard to imagine that there's something that distinguishes between polynomials, cubic polynomials that have a marked critical point of period K. So it's natural to conjecture that your curve determined by that condition is just one piece, one irreducible piece, one connected piece. And more or less, that is one way of seeing it, more from the dynamical point of view. Another way of seeing it is that if you choose at random a polynomial in 2 variables, most likely you're going to get an irreducible polynomial. So why should the polynomials that determine the equations of these curves be not so random? So that is to motivate the question of irreducibility. Okay. So let me now go to the periodic curves. As you will see, and if you have good memory, these are not the same numbers that Araceli gave, but it is because there's a minor difference between the curves that Araceli considered and the ones that I'm talking about here. But I will be more specific in a little while. So for low periods, you compute and you get, well, Jack computed, and you get that these curves are these guys. So the period 1 is just the complex plane. The period 2 is the complex plane, the punctured complex plane. Period 3 is the complex plane with 5 punctures. And then you work more, I guess, that now computers can do that, but Mathieu talked about, well, to see that this is a genus 6 surface with 14 punctures. Okay. Okay. So so one interesting thing here, and that Araceli talked about, is that once you start growing the period, the topology, the genus of the surface, gets larger and larger and larger, and the number of punctures get larger and larger and larger. So these are dynamical systems. I mean, these are parameter spaces, which, although they are one-dimensional as the quadratic family, which is parameterized just by the complex plane, right? They still are one-dimensional, but what is interesting is that they have non-trivial. They start having non-trivial topology. Okay. And well, what we know is that the Euler characteristic can be computed for the can be computed, but the genus, but in order to be able to compute the genus, you have to compute the number of punctures. And there's an algorithm to compute the number of punctures, but well, we have no general formula for the number of punctures. But we know that the genus grows when the period grows. And so one important question here is to understand the fundamental group of these
punctures.
Huh?
30.
Of these surfaces of this. And what Araceli talked about, I think that goes sort of a program to try to understand the fundamental group. And but what we did with Mathieu is something previous to that, that is, well, is it connected or is not connected? Okay. But it would be very interesting to understand, and it is really what I mean. What I find fascinating about these parameter spaces is that they have non-trivial topology, and how to understand these non-trivial topologies. It's not clear. Okay, so now let me try to tell you about the two movements. That is how we prove that the periodic curves are irreducible. So for that, we follow Jack's parametrization, which is to talk about curves, to talk about general results is better to talk about moduli spaces, but to work with the curves explicitly is better to have them have every point in the curve determine a unique dynamical system and so on. So to be a parameter space. And that can be done passing to a double cover. And this is what I'm going to remind you what it's about here. So we work with an explicit family of cubic polynomials, which are the polynomials of this form. The only difference with Araceli's talk is that Araceli used a capital F, an uppercase. So this is the family, depends of two parameters, A and V, which live in the complex plane. The critical points of this polynomial are plus and minus A, plus A, let me emphasize this here, is the marked critical point. And minus A is the free critical point. The marked critical value is the image of the marked critical point. And two marked cubic polynomials here are equivalent if and only if they're related by the involution minus A minus B. A goes to minus A. So they're so now in this space, where for each parameter AB, we have a unique polynomial FAB, the corresponding periodic curve is consists of all polynomials where plus A has period K. And remember that going from this parameter space to moduli space, we have an involution, and that translates into the fact that this mu S K is going to be a double cover of this one, and it's not difficult to show that one is connected if and only if the other one is connected, and one is irreducible if and only if the other one is irreducible. And here you can compute explicitly which are the polynomials, well, for low degrees, which are the polynomials that so this here is given by an equation, phi sub k, you can compute a polynomial so that the locus, so that the vanishing locus of the polynomial is exactly sk. Okay, so our job now is to prove that these guys are connected. So I guess that you started on Monday, on Thursday, you don't need to be reminded, but I'll do it again. So the field Julia set, just to fix notation, is going to be K of F. The Julia set is J of F. And the basic dichotomy is that you have the connectedness locus, where the Julia set is connected. That means that the free critical point doesn't go to infinity because the other critical point is periodic, so it's always non-escaping. And the escape locus is where the free critical point escapes to infinity. Important thing is that, so you have your surface here. I mean, you might have several components like this inside your AB in C2. And the connectedness locus is somehow in a compact part of this surface. And the escape locus is an open set and is unbounded. Every connected component of the escape locus is unbounded. The same pictures in Mathieu. This is the curve S1, where you have the Pacific Ocean is the escape locus, and the I don't know, the island is the connectedness locus. This is, I'm a bit cheating you because this is a picture in the quotient by the double cover, and I did the definitions upstairs. Similarly, this is a picture of S2, which is a punctured plane. The puncture here is here. And it has two escape, the escape locus is this part here and this part here. And this is S3. Again, I'm talking in in this space. It has six punctures. This, an infinity, and around each puncture you have a, I don't know, you have a part of the escape locus. Here you have part of the escape locus. You see that there are 6 components. Okay. So each escape region definition. Escape region is a connected component of the escape locus. And this is more or less all, some of the things we need to know about the escape locus. All the dynamical systems in the escape region are hyperbolic, which is the nicest type of dynamical systems. Every escape region is conformally isomorphic to a puncture disk. As you see here, the region, the connected component of the escape locus is a puncture disk. The punctures correspond to ideal points at infinity, and every connected component of this algebraic curve has to contain an escape region because every connected component of escape is unbounded in C2, and the connectedness locus is bound. This is compact. So the strategy to show that escape is irreducible, since you know that every component contains some escape region, is to start that escape region and then move to another escape region and then move to another escape region. And within the curve escape, and hopefully be able to join all the escape regions of escape. So that is going to be the strategy to show that escape is connected, is to connect all escape regions. And for that, we need to have a crude invariant of each escape region. And to have a crude invariant of each escape region, we need to understand a little bit about the dynamics of polynomials that are in escape region. So I guess many pictures are stolen either from Jack or from Matthias or Araceli. So this, I think, is from a paper by Jack. So, so in each escape region, we're going to use itineraries to classify escape regions. Itineraries will come out of looking at the green function. The green function of a polynomial f, it measures the escape rate of points in the basin of infinity. And when you are in escape region, minus a escapes to infinity, and there's the curve of all the things that escape at the same rate. Is a figure 8, like this one, which separates 2 disks, one disk which we're going to call D0, and one disk that we're going to, the smaller disk that we're going to call D1. There is the disk D0 is going to be the one that contains the critical point plus A, which in this case is a point over there. So whenever you have a polynomial in escape region, you have that the critical point minus A escapes to infinity, and you have this figure 8. The important thing here is that the disk that contains the critical point plus A maps onto the image that is a disk like I drew it as a 2-to-1 map, and this disk here as a 1-to-1. Okay, so once you have this, your field Julia set is going to be all contained in this, in the union of these two disks, the 0 and the 1, and given a point in the field Julia set, is going to, when you apply the function, is going to jump between these two disks, and you, what you do is you record the itinerary of that point by a symbol sequence in zeros and ones. So, for example, here's the, this is an element of S6, okay? And the critical orbit is labeled, and you can assign to the critical orbit an itinerary. I'm going to look at the itinerary of the critical value. This guy here is critical value. So if you look at the itinerary of the critical value, A1 is in the 0 side, so it starts with 0. Then A2 is in the 1 side, continues with 1. A3 is in the 0 side, continues with 0. A4 is in the 0 side, continues with 0. A5 is back in the 1 side, in the 1 disk, and A6 is 0. And then it repeats periodically because then it comes back to A1. So the itinerary of the critical value is 0, 1, 0, 0, 1, 0, 0, 1, 0, 0, and 0, and so on. Okay. Okay. And what you need to know is that the itinerary of the critical value, of the marked critical value, which is going to be a symbol sequence that repeats every k digits. It could repeat more often, but at least it repeats every time you come back to the critical value, it starts repeating the symbol sequence. So you look at the itinerary of the critical value, and that itinerary is independent of the point where you are in the escape region. And that itinerary, I mean, the first k symbols of that itinerary is called the needing word. We call it the needing word. Then the itinerary of B is going to be the needing word repeated infinitely many times. And okay, so to each escape region, there's a very crude invariant that you can assign, which is the needing word, which encodes the itinerary of the critical value that has period k. And that is a label for the escape region. And there is, so you can compute, well, Jack did, computed how many regions there are with the same itinerary. And essentially is, maybe I forgot to say something. So when you have the itinerary of the needing word of the critical value, it always has to finish with a 0, because the critical value in k-1 iterates, this is f to the k-1 of b, has to be equal to the critical point, which is always in the disk, the 0. That's how we define the zero. We define it as the disk containing the critical point. Okay. So so you essentially the formula given by Jack is that if you look at the number of zeros, with the exception of the last zero, you take 2 to that number, and that will give you, counting with certain multiplicity, the number of regions that have that needing word. So there's one distinguished needing word, which is of the form 1k, 1 repeated k minus 1 times, and then a 0, that for which there exists only one region counted with multiplicity. So there's this very special needing word where you know that there's only one guy, one region that has that needing word. So the strategy to prove that the curve SK is connected is you start at any component. That component has to contain an escape region, and then you try to move to another escape region which is closer to this distinguished one, to one having this needing word, 1 to the k minus 1, 0. And here is where the two moves that I was talking about at the beginning of the talk. So we do that making two types of moves, what we call the type A move and the type B move. The type A move, let me describe you type A move and type B moves between needing words. Okay, so to describe you that, I need to first tell you what the maximal return time to the 0 is. So if you have any point in the, so you have plus A, which is A naught. If you have any point in that orbit, since that is in the disk D0, then AJ maps somewhere in this side on this other side, but eventually has to return to the side 0, since the critical point is always in that side. So the number of iterates that somebody in the disk D0 takes to return to the disk D0, that is called the return time to D0. And there are some elements in the orbit of the periodic period K, which have maximal return time. So let me go back here. For example, in this case, the elements of the orbit in this period 6 case, the elements of the orbit that have maximal return time are exactly the critical value. This is A1, 2, 3, 4, and A4. Because they take 2 iterates, takes for them 2 iterates to come back to the disk D0. All the other elements in the orbit, in the periodic critical orbit, have the next iterate, take 1 iterate to return to D0. For example, if you are, I don't know, A3 comes back immediately to D0, while A4 goes to A5 and then to A6, takes 2 iterates to come back to D0. So there's some elements in the periodic critical orbit which have maximal return time, and those are going to be the important elements for us. And maximal return times are, if the maximal return time is mu, you identify those elements because in the needing word you have something like this. This corresponds to AJ with maximal return time. So the way we are going to connect escape regions, we start at escape region with certain needing word and with certain maximal return time. And we're going to apply type A or type B moves. We don't know if we are going to apply a type A or a type B. We don't know. I mean, there's some. We only know that we apply these moves. So we only know that we will travel from. Either we travel from the escape region U to escape region U prime, this with a needing this, and this with another needing, via a type A or a type B move. The only thing that we're going to know about the new escape region is that its needing word is obtained by one of these two moves. And let me explain what the moves are. So we assume that mu is the maximal return time, and a type A move is going to happen if the critical point has maximal return time. Then the move consists on switching a string of ones by a string of zeros followed by a one. So in this case, the critical point 0, the critical point plus A, spends a lot of time here and comes back to A mu. Okay? And then this is the needing word corresponding to kappa, and a move in the word is going to switch all those to something that does like this. It stays a lot of time here and then moves to the other side.
So Jan, you do that for every zero that appears there.
So only
in the beginning.
Only in the beginning, and we have no control. So a type A move is going to start with a word like this. So it's a move on the words. I'm just trying to give you the intuition what it means in the dynamical systems, but it's a move in the words. You have a word where your maximal string of ones could appear several times in the word, but it has to appear it appears in the initial segment with 1 to the mu minus 1, 0. And a word obtained by a type A move from the word kappa is by definition a word kappa prime, where you replace all the initial ones by a 0, the next 0 by a 1, and then, I don't know, something happens here. You could do whatever you want, okay? That is a type A move, okay?
Yes, thank you.
And a type B move is you have your word kappa, your initial word kappa, mu is the maximal return time, and you switch somewhere in the word you have 0, 1 to the mu minus 1, that is this guy is something with a maximal return time, and you just switch it by a 1. So now you have a string, a longer string of ones. So if you start with any word, which is not of the form 1k to the minus 1, 0, and you apply either a type A move or a type B move certain number of times, you are forced to reach to this distinguished word. That is not a difficult exercise. So, okay. So I don't know, I think that, let me just fix ideas. there's given a word in k bits. There are two type of moves, type A move and type B move. And if you make these moves with all the choices involved in any order, just make a move and then make another move, etc., etc. Eventually, you reach the distinguished word. Okay, so why these moves are called type A and type B? Because these moves that we make in the words are associated with crossing certain type of hyperbolic components. So in order to motivate that, let me go back to this picture. Remember that the distinguished word is something with, in this case, for example, the distinguished word of period 6 is 1 to the 5, 0. And we want to start with a dynamical system like this one and go towards a dynamical system where you have all the iterates here and the critical point alone in the 0 disk. So what one wants to do is to start moving A1 to this side, A4 to this side, A3 to this side, so to leave alone this guy. That is a naive way to see it. But to move things to this side, this is very naive, intuitive idea, one has to cross minus A. So there are going to be iterates of the periodic critical orbit, which somehow have to go through minus A. Of course, we cannot move points in the periodic orbit to the other side without crossing the connectedness locus, because within escape region, we have the same needing word. Okay. So when we cross the connectedness, in the connectedness locus, there's this interior components, which are very important, which are the hyperbolic components, when both critical points are attracted to an attracting periodic orbit. And these hyperbolic components are classified in this 4 types: adjacent, bitransitive, capture, and disjoint. Adjacent is when the 2 critical points are in the same component. Bitransitive is when you have one component with plus A, another component with minus A, and these are mapped to each other. And capture and disjoint are not going to be important for us, but A and B are the important ones. And each of these hyperbolic components contain a center, which is a unique post-Grignard finite map. Well, there's a unique post-Grignard finite map in each of these hyperbolic components, which is called the center of the hyperbolic component. In the bitransitive case, that means that A eventually maps to minus A, and minus A eventually maps to A. And in the adjacent case means that the A is periodic. So this is a picture from Jack's paper. This is the S3. And if you look, the hyperbolic components of type AB are labeled. I think that all of them are labeled. Or maybe, I don't know if there's one here, but okay. And as you see, they play an important role in connecting the escape regions. So you somehow intuitively you see that A, if you are in this exterior region, you can try to cross A to lead to these other 2 regions and so on. So it seems like from adjacent and bitransitive components, you can sort of dive in different escape regions. And the first thing that we do is to sort of analyze that. So I will do this by example. So this is an adjacent map where this is A equals minus A and maps to the critical value there. I have a picture here to be sure. A1 is here. This is minus A and A. This is an adjacent center, and this is a bitransitive center. The two critical points are in the same or so in order to, if we go back in parameter space, these are, okay, these are, this is a parameter here and here. The adjacent parameter corresponds to the center of this adjacent component, and the bitransitive picture corresponds to that. And I want to illustrate to you how from the bitransitive one can go into these two regions, and from the adjacent one can go into these three regions if one bifurcates appropriately from the hyperbolic component. Okay. And let me just label you the meeting words of these regions. This is 010. This is the airplane. This is 10. Okay, external rays. I don't think that I need to remind you what external rays are. And let me skip this because you've seen a lot of talks. So when I talked about the needing word was introduced thanks to the fact that for escape region, thanks to the fact that the critical point minus A was escaping to infinity, and there was a disk here, D0, and there was a disk here, D1. But when you're in the connectedness locus, you no longer have these two disks because your Phil-Julia set is connected. So, and you don't have the escaping critical point. So it is more convenient to keep track of the needing word by the gradient flow lines or the parametrization that you have these. So here's the unit disk, and here you have a so the Bether map, which is what conjugates the dynamics of the polynomial with C maps to C cube, works from the level of the escaping critical point up. So there are two radial lines that crash with the critical point minus A. And these two lines have to map to exactly one line. So if this angle is theta, oh, I wrote it wrong. Angle is theta minus 1/3, so, or theta prime. What happens is that these two angles have to map to the same angle under multiplication by 3. So they differ by plus minus 1/3. Equal to theta prime is equal to theta minus 1/3, or if it was here, to theta plus 1/3. So a way to see, to understand the needing word in terms of external rays is to look at the two external rays that crash against the critical point minus A, and see that chops the complex plane into two regions, one where there's going to be the disk D0 and one where there's going to be the disk D1. So you can now look at the itinerary according to these two regions of the plane, rather than looking at the disk D0 and D1 you can look at the region of the plane cut by theta and theta minus 1/3 that contains the critical point plus A, and the one that doesn't. So when you do that, the situation is the following. So let me try to illustrate. So remember that this is a type B center. And you want to understand which escape regions touch the hyperbolic component that is centered at this type B center. And what you want to do is you realize that here there's minus A, which is equal A2. So the corresponding Fatu component maps 2 to 1 onto the next Fatu component, which is this one here. So there are going to be two rays which map onto the same ray. I think that this one, theta minus 1/3. And then what we do is we show that when you have this configuration, this theta has to be chosen so that is supporting blah, blah, blah. So some technical conditions that you can choose a way of exiting the hyperbolic component centered at this polynomial so that you have minus A there, theta minus 1/3. Here you have the same thing, theta minus 1/3. And if you look closer here, we have plus A. If you look very close here, you recognize that here's an airplane. And this is because here's plus A, here's A1, and here's A2. And what is happening here is that here's plus A, here's A1, and here's A2. So let me try to. So we show that whenever you are in a type B hyperbolic component, you can make a choice of these angles, and you can make a choice of a way of going to the boundary of the hyperbolic component center here, so that if you dive into escape region where you have the A2, because here minus A was equal to A2, being in this side, and there's another choice where you have the A2 being in the other side. So in this case, we have a needing word because the corresponding now the corresponding picture for the disk are like 0, 0, and here the needing word is 0. No, the needing word is 0, 1, 0. And that is essentially the type B move. We were able to move an A2 that was in the 0 side to an A2 that was in the 1 side. So when we go through a type B component, we are able to, and the type B component is determined because the jth iterate of the mark critical point is a critical point minus A, we are able to change that symbol from a 0 to a 1 or a 1 to a 0 indistinctively. And well, I don't know if it's, and we can do something similar for type A components. In this case, here's A0, here's A1, and here's there, that one's A2. And we can make choices, appropriate choices. Even we have an angle here. Well, so remember that a type A component is centered at a polynomial where minus A is equal to plus A. So this component maps onto its image by a map that is 3 to 1. So there are 3 rays. The map onto the same ray there. And you can have to choose them so that they are supporting and something like that. Technical condition. And then the idea is that you can, we show that you can exit the corresponding type A hyperbolic component so that minus A is going to be there. So theta is 2/3. And here is going to be A0 and A2. That is if we choose this, so we can, so there's one way to exit so that this becomes D1 in certain sense. There's one way to exit so that this becomes D1. And there's another way to exit so that this becomes D1. That is the other exit would leave A2 here, A0 here, and A1 here. This is this way. There's another way to exit so that corresponding picture. A2, A1, and A0. This is here. So if you, this is going to correspond to the needing word 0, 1, 0. This is going to correspond to the needing word 1, 0, 0. And this is to 0, 0, 0. And if you go back to the picture of the corresponding parameter space, you see that effectively from that adjacent component, you can dive into a 0 bar, a 1, 0, 0, and a 0, 1, 0. So, so the first part of moving between escape components comes out of analyzing what you can do if you're in a bitransitive component or in an adjacent component, which ways you have to go into escape regions. And the other part of the proof is to say, well, if you start in escape component, in escape region, how do I go to a type A or a type B component? How do I move from escape region U to a type A or type B component so that I can exit to a component U prime so that the needing word is obtained from kappa U. The needing word of kappa U prime is obtained from kappa U by a type B move or a type A move. And that is the difficult part of the, I mean, I don't know if the difficult part, but that is this is the part that is more subtle of connecting things, is that you can go from any escape region to some type A or type B component that are convenient to cross and obtain a needing word that is given by a type A or B move. And the way we do that, just to is to do this is to via array connections. So array connection is the following. I told you that you always have arrays that come and bounce off the critical point minus A. And then array connection is something like this. You can continue the array. And that continues to bounce, okay? An array connection is when you can continue the array that bounce off minus A so that you reach very close to one of these guys, one of these components, but one of these critical points. More precisely, array connection is array that bounce off minus A and if you zoom in the component that contains a point of the critical orbit, you want to land this array. You want the array to land in the boundary of the Patu component that contains the element of your critical orbit. And the main lemma that we prove, the main combinatorial lemma that we need to make things work, is that given any escape region, which is undistinguished, there is a connection, array connection, so that the AJ where you land is has maximal return time. And once we do that, we can use that array connection to go to a type A or B component to make a type A or B move, to move to escape region which has a needing word obtained by a type A and B move, and then repeat the argument. Look for array connection, which has maximal return time, move to a type A, B component, and then cross. I think that is all that I want to say. Thank you.
Thank you very much, Professor Kiwi, for your talk. And then it's time for the audience to share their questions. Is there any question about the presentation?
I have a question about, so this works for all the escape, for all the SPs, right? For P greater than 2, because you always have a component that is going to escape component of the type 1K0. In S1, you only have a zero escape region.
Yes, but in S1, you know that is connected.
Okay.
I mean,
okay, so this is for SP P greater or equal than 2.
Yes. I mean,
yeah. Okay, good.
Yeah. So if you look at the well, I don't know if S1 is sort of weird because 1K to the minus 1. Yeah.
Okay, thank you.
Thank you. Is there any questions? Any other question? Remember that you can also write down your questions in the Zoom chat. Okay, if there's no more questions, we thank Professor Jan Kiwi again for his time. Thank you very much, Professor.
Okay. So what is...
Who was helping you to give the talk? There was a dog there.
I actually have a dog, and there's my neighbor's dog that also comes here.
Okay.
And it was my neighbor's dog.
I thought it was your dog. I said, oh, Jan has an assistant.
Yeah.
Okay, very good. So,
so why is called the 38 movements?
Well, I'm not sure, but I think Alex is more capable to answer that question.
Que Alex no quiere contar.
Alex no quiere contar. Bueno, yo soy invitado, no, entonces no sabría decirle.
Alex, ¿estás ahí? Alex,
Sí,
ahí.
estoy aquí.
Ver, cuéntanos. ¿Por qué?
Es algo largo, pero vamos. Okay. Bueno, cuando tenía la idea de hacer esto del seminario, yo ya, bueno, estaba pensando en el nombre, ¿no? Y yo quería algo así como que el nombre tenga un número y que, no sé, y que tenga, no sé, un número interesante, ¿no? Estaba pensando en el libro este libro de ciencia ficción de Douglas Adams, la guía del autoestopista galáctico, donde dice que 42 es la respuesta más profunda a la vida, al universo. Estaba pensando en eso y también estaba pensando en 1729, algo así. Eso tenía en mente. Pero bueno, y algo así, claro, algo así. Eso es lo que pasó. Sí, miré la talla del calzado y pasó. Quise ser más profundo que como lo que menciono, pero fue apenas eso.
Ok.
Yo creí que tenía que haber algo con música. Cuando vi 38 movimientos.
Sí, bueno, hay razones para pensar eso. También piensan que es con respecto a ajedrez o alguna idea filosófica más profunda.
Ajá, ok.
Justo eso me pasaba por la mente, igual pensé que era algo así como 38 movimientos para ganar en un juego de ajedrez.
Bueno, sí. Es como menciona el profe Maffi, es tal cual.
Ok. Muy bien.
Okay, very good. Thanks again to everybody that has attended to this session. And this was our last meeting of today. So we're going to meet again tomorrow. Okay, so remember that you have all the schedule of all the talks in the web page, and also you can find these videos, the recording in the in YouTube. So you can see it again later. Thank you very much to everybody, and we see you tomorrow. Goodbye.
Bye, thank you.